Hello there, and welcome to Physics with William, where curiosity gets comfortable, complicated ideas are given room to breathe, and science takes the slower route through the evening. Tonight we're going to meet one of the strangest atoms in nature. It has no nucleus. It contains almost no matter in the ordinary sense. It survives for only a tiny fraction of a second, and when its brief existence comes to an end, the entire atom disappears. Not breaks apart, not changes into a different element, disappears. Its name is positronium, and it is formed when an electron meets its antimatter counterpart, the positron. Instead of immediately destroying one another, the two can sometimes become bound together. For a short while, they circle around their shared centre, held together by electrical attraction. They behave enough like an atom that physicists gave their partnership a name. Then, sooner or later, the electron and positron annihilate each other and turn their energy into particles of light. It is an atom that carries the cause of its own destruction inside it from the moment it forms. That sounds rather dramatic for something so small. Most atoms are content to remain in a table, a chair, a cup of tea, or perhaps a biscuit that has been left dangerously close to the edge of a plate. Positronium has no such long-term plans. It appears, follows the rules of quantum physics for an extremely short time, and then removes itself from the universe with remarkable efficiency. Before we look more closely at this unusual object, I would love to know where you're listening from tonight. Are you somewhere quiet with the lights low and the day nearly finished? Is it late evening, early morning, or one of those uncertain hours when checking the clock only seems to make things worse? You might even be listening in a room filled with ordinary atoms. The walls, the floor, the bed, the device playing this video, and your own body are all built from matter that has existed for years, centuries, or far longer. Somewhere inside a laboratory, however, a positron may be slowing down through a material, searching without intention for an electron. If the conditions are right, the pair may form positronium, remain together for less time than you could possibly notice, and vanish before anyone has the chance to become properly acquainted with it. If you find this kind of quiet, scientific wandering soothing, or simply enjoy meeting parts of the universe that seem to have been designed by someone with an unusual sense of humour, you can give the video a like and subscribe to the channel. It helps this calm corner of physics reach other curious minds, including those who prefer their antimatter delivered at a sensible volume. For now, settle into whatever position feels comfortable. There is no need to remember every term. Nothing here will be followed by an exam, a surprise quiz, or a laboratory assistant appearing beside the bed with a clipboard. We can take our time, which is fortunate, because positronium itself has very little of it. To understand why physicists find positronium so useful, it helps to begin with the ordinary atom. Most of the matter around us is made from atoms containing a central nucleus. That nucleus contains positively charged protons and, in most cases, electrically neutral neutrons. Negatively charged electrons are found around the nucleus, occupying quantum states that are often described as orbitals. The picture is sometimes simplified into something resembling a tiny solar system, with electrons circling a nucleus like planets around a star. That image is not quite correct, but it can be a useful first step. Real electrons do not follow neat little paths with clearly marked lanes. Quantum mechanics describes them through probabilities. We can predict where an electron is likely to be found, but not assign it a miniature schedule and ask it to report to one side of the atom at precisely 9:30. Even with that complication, the basic structure is familiar. A heavy nucleus sits at the centre, while much lighter electrons are bound to it by electrical attraction. The positive charge of the nucleus attracts the negative charge of the electrons. Hydrogen is the simplest example. An ordinary hydrogen atom contains one proton and one electron. The proton forms the nucleus. The electron is bound to it. Because hydrogen has only two main particles, physicists have studied it in extraordinary detail. It has become one of the standard testing grounds for ideas about atomic physics and quantum theory. Positronium looks similar to hydrogen from a distance, at least in a mathematical sense. It also contains one negatively charged electron bound to one positively charged particle. But the positive particle in positronium is not a proton, it is a positron. A positron is the antimatter counterpart of the electron. It has the same mass as an electron, but the opposite electrical charge. The electron is negative, the positron is positive. Apart from differences connected to charge and a few related properties, they are matching particles. This makes positronium very different from hydrogen. In hydrogen, the proton is much heavier than the electron. The proton sits close to the center, while the electron occupies the surrounding region. In positronium, both particles have exactly the same mass. Neither one can be treated as a heavy, nearly motionless center. Instead, the electron and positron move around a point between them. There is no nucleus. That single fact already makes positronium unusual. We often define an atom by the presence of a nucleus, yet here is something widely described as an exotic atom even though its center is empty. The electron and positron are simply bound to each other. Each is attracted to the opposite charge of the other, and both take part equally in the motion. You could imagine two dancers of equal weight holding hands and moving around the middle of the space between them. Neither dancer remains fixed while the other does all the work. The shared center stays in place, while both partners move. The comparison is imperfect, as comparisons involving quantum particles usually are. Electrons and positrons do not have shoes, do not need music, and are unlikely to complain that the other one keeps missing the beat. Still, the important point is that positronium has no heavy central object. It is a balanced system made from two equal particles. This balance makes it scientifically valuable. Many atoms are complicated. They may contain several protons, several neutrons, and many electrons. All those particles interact. The nucleus has an internal structure of its own. Electrons affect one another. Calculations become difficult, corrections accumulate, and before long even a confident physicist may begin staring at a whiteboard as though it has committed a personal betrayal. Positronium is simpler. It contains only an electron and a positron. Both belong to a family of particles that, as far as current experiments can tell, have no smaller internal parts. There are no protons or neutrons inside the system, so there is no nuclear structure to complicate the picture. That does not mean positronium is easy to understand. Quantum physics rarely offers anything quite so generous. The electron and positron interact through the electromagnetic force. Their motion must be described using quantum mechanics. Their antimatter relationship allows them to annihilate. Tiny effects connected to the vacuum, relativity, and particle interactions all influence the details. Even so, compared with larger atoms, positronium is remarkably clean. It gives physicists a system in which the rules can be tested with fewer distractions. The word clean is often used in physics to describe an experiment or object that allows a clear comparison between theory and measurement. It does not mean that positronium has recently been dusted or placed in a well-organized cupboard. It means scientists can calculate its behavior with great precision and then compare those predictions with what instruments observe. Any disagreement may reveal that a calculation is incomplete, an experiment needs improvement, or something unexpected is affecting the particles. This is one reason positronium has attracted attention since it was first observed in the 20th century. It is small, temporary, and difficult to handle, yet it can reveal whether some of our most successful theories are describing nature correctly. Its brief lifetime is not an inconvenience added to the story. The brief lifetime is one of the main features. An electron and a positron are allowed to annihilate because they are particle and antiparticle. When they meet in the appropriate quantum state, their mass and motion can be converted into other forms of energy. In ordinary positronium annihilation, that energy is usually carried away by particles of light. The exact details depend on the state of the positronium. The electron and positron each possess a quantum property called spin. Spin is not quite the same as a ball physically rotating, although the word encourages that image. It is a built-in property of the particle, and it affects how particles combine and interact. The spins of the electron and positron can be arranged in different ways. Those arrangements produce two main forms of positronium, and the forms do not survive for the same length of time. They also do not usually decay into the same number of light particles. We will come to those differences carefully, because they are central to understanding how positronium behaves. For the moment, it is enough to know that this atom has more than one possible internal arrangement, and those arrangements determine how quickly the final annihilation occurs. One form lasts for roughly 1/10 of a billionth of a second in empty space. The other lasts for a much smaller fraction of a billionth of a second. Both are far too brief for human senses. A blink takes an enormous amount of time by comparison. A camera shutter would appear almost permanently open from the point of view of positronium. Even a beam of light can travel only a modest laboratory distance during the lifetime of the longer-lived form, yet short does not mean unimportant. Many events in particle physics occur on timescales that seem almost non-existent to us. Modern detectors can record the results. Electronic timing systems can compare arrivals separated by tiny intervals. Repeated experiments can produce millions of positronium atoms, allowing scientists to build a clear statistical picture from objects that individually vanish almost as soon as they appear. It is a little like learning about sparks. A single spark is brief, but if you can produce and observe many sparks under controlled conditions, you can measure their brightness, colour, timing, and behaviour. You do not need to persuade one spark to remain in the laboratory until Thursday afternoon. Creating positronium usually begins with a source of positrons. Positrons can be produced in several ways. Some radioactive materials release them during particular forms of nuclear decay. High-energy collisions can also create electron and positron pairs. In specialized facilities, beams of positrons can be guided toward carefully chosen targets. Once a positron enters matter, it loses energy through interactions with the atoms around it. It may scatter, slow down, and eventually encounter an electron. In many cases, the positron annihilates without forming a lasting bound state. Under suitable conditions, however, the electron and positron briefly become positronium. The surrounding material matters. Empty spaces inside solids, the structure of molecules, temperature, pressure, and chemical environment can all influence whether positronium forms and how long it survives. That sensitivity has turned positronium into more than a subject for pure particle physics. It can also act as a probe of materials. Because positronium is so small and reacts strongly to its surroundings, its lifetime can provide information about tiny gaps inside a substance. These gaps may be far smaller than anything visible through an ordinary microscope. By measuring how quickly positronium disappears, researchers can learn about pores, defects, and empty spaces within polymers and other materials. In that role, the self-destroying atom becomes a kind of temporary visitor. It enters a microscopic space, survives for a measurable interval, and then annihilates. The timing of that disappearance tells scientists something about the room it briefly occupied. This is an unusual method of inspection. A building surveyor normally prefers not to vanish in a flash of light after measuring the cupboard under the stairs. At the atomic scale, however, the approach can be very effective. Positronium is also connected to medical research. Positrons are already used in a form of medical imaging known as positron emission tomography. In that technique, a radioactive tracer releases positrons inside the body. Those positrons eventually annihilate with electrons, producing light particles that can be detected outside the body and used to reconstruct images. Researchers have been exploring whether information connected to positronium formation and lifetime could provide additional details about biological tissue. This does not mean hospitals are currently filled with doctors asking positronium for a second opinion. It means the behavior of positrons before annihilation may contain useful information that conventional imaging does not fully capture. The same object can therefore sit at the meeting point of several fields. It belongs to atomic physics because it forms bound states. It belongs to particle physics because it contains antimatter and ends through annihilation. It belongs to quantum theory because every stage of its existence depends on quantum rules. It can assist materials science, and it may contribute to new methods of medical imaging. All of that comes from a structure containing only two particles. There is another reason positronium captures attention. It places matter and antimatter in direct contact without immediate destruction. Popular descriptions of antimatter sometimes give the impression that matter and antimatter must annihilate the instant they come anywhere near each other. The truth is more precise. An electron and positron can interact in several ways. They may scatter apart, they may annihilate, they may form a temporary bound state before annihilation. Positronium is that pause. It is not a stable peace agreement. The final outcome is still built into the system, but for a short interval, the opposing particles form something organized. They occupy quantum states. They possess measurable energy levels. They can absorb and emit radiation. They can be produced in excited forms. Under special laboratory conditions, groups of positronium atoms can even be studied in ways that bring them close to collective quantum behavior. The atom is doomed, but it is not inactive. During its short existence, positronium follows a detailed set of rules. Those rules are predictable enough for physicists to calculate and subtle enough to expose extremely small effects. Its energy levels resemble those of hydrogen, but they are not identical. The equal masses of the electron and positron change the structure. Annihilation adds effects that hydrogen does not possess. The two spin arrangements divide the system into distinct forms. Interactions with surrounding matter can alter the observed lifetime. Each detail offers a test. When researchers measure the gap between energy levels, the rate of annihilation, or the properties of emitted light, they are checking whether theory and nature agree. Most of the time, the agreement is impressive. Occasionally, measurements and predictions have appeared to differ, leading to years of improved experiments and more careful calculations. This is how science often moves forward. Not through one dramatic announcement delivered beside a machine making encouraging noises, but through repeated measurements, corrected assumptions, better instruments, and several people asking why the final decimal place is behaving strangely. Positronium is especially useful for testing quantum electrodynamics, the theory describing how electrically charged particles interact through the electromagnetic field. Quantum electrodynamics is among the most accurately tested theories in science. Its predictions can agree with experiments to an extraordinary degree. That success does not make further testing unnecessary. A theory that has passed many tests becomes more valuable when it passes new kinds of tests under different conditions. Positronium provides conditions that ordinary atoms cannot. It contains a particle and its antiparticle. Both have equal mass. Annihilation contributes directly to its behavior. There is no nucleus to introduce uncertain size or structure. If a previously unknown particle or force interacted with electrons and positrons, it might leave a tiny trace in positronium measurements. No such discovery is guaranteed, and careful scientists do not treat every small disagreement as evidence of a new universe hiding behind the equipment cabinet. Still, precise systems are where subtle new effects might first become visible. This gives positronium a curious position. It is simple enough to calculate, difficult enough to remain interesting, brief enough to seem almost unreal, useful enough to keep entire research programs occupied. The name itself can sound like an element from a science fiction story, perhaps one stored in a glowing container that should definitely not be touched. But positronium is not a fictional substance or a newly proposed particle. It is a real bound state that has been created and measured many times. It does not appear on the standard periodic table because it is not an element. Elements are defined by the number of protons in their nuclei, and positronium has neither protons nor a nucleus. Calling it an exotic atom is a convenient way of describing its atom-like behavior. Other exotic atoms exist as well. Some replace an electron with a heavier negatively charged particle. Some contain antiparticles. Some are built from combinations that survive only briefly. Studying them allows physicists to isolate particular interactions and compare different parts of theory. Positronium may be the lightest of these atom-like systems. Its total mass is only the combined mass of an electron and a positron. That makes it much lighter than hydrogen, since even a single proton is far heavier than an electron. Its lack of a heavy nucleus also means that the centre of the system is shared equally. Every description has to respect the motion of both particles. There is no central anchor quietly carrying nearly all the mass. This becomes important when we ask how positronium forms, what its size is, how its energy levels are arranged, and why its two main forms decay so differently. Those questions lead naturally back to the particles themselves. The electron is familiar because it is present in every ordinary atom. It helps determine chemistry, electricity, bonding, and the structure of matter. The positron is less common in daily life, but it is no less real. It appears in radioactive decay, cosmic ray interactions, high-energy experiments, and medical technology. Bringing the two together creates an object that resembles an atom and behaves like a countdown. There is no visible clock attached to it. The particles do not know how long they have. Quantum theory describes the probability that annihilation will occur during a given interval. One positronium atom may vanish sooner than another prepared in the same state. Across a large group, however, the average lifetime follows a reliable pattern. That mixture of uncertainty and predictability is typical of quantum physics. Individual outcomes are not always fixed in advance, but the behaviour of many repeated events can be calculated with great accuracy. A single radioactive atom cannot tell you exactly when it will decay. A large collection follows a dependable statistical curve. Positronium behaves in a related way. Its annihilation is inevitable, but the precise instant for one particular atom is not assigned like an appointment. No tiny calendar appears with the message "annihilation scheduled for shortly after lunch." Instead, physicists speak in terms of probabilities and average lifetimes. As we move further into the story, we will look at how the positron was predicted, how antimatter entered physics, and how an electron and positron can become bound rather than annihilating immediately. That will take us closer to the unusual structure of positronium and to the reason a system with no nucleus can still behave like an atom. For the moment, the central picture is simple enough to hold. One electron, one positron, equal masses, opposite charges, a temporary bond, then light. Between their meeting and their disappearance lies a complete piece of atomic physics, compressed into less time than the nervous system could ever register. It is brief, but it is not meaningless. Every instant of that existence follows laws that connect matter, antimatter, light, probability, and the structure of empty space. To see how such an object can form at all, we need to look more closely at the unusual relationship between the electron and the positron. Two particles that mirror each other closely attract one another strongly, and carry within that attraction the possibility of both an atom and its end. The relationship between the electron and the positron begins with a striking similarity. They have the same mass, they possess the same amount of spin, which is an intrinsic quantum property, rather than the ordinary spinning motion of a tiny ball. They respond to the same basic laws of quantum physics. Place either one in an electric or magnetic field, and its motion can be predicted using the same framework. The important difference is electrical charge. The electron carries negative charge, while the positron carries an equal amount of positive charge. Other particle properties that distinguish matter from antimatter are reversed as well, but the opposite charge is the difference that matters most for the formation of positronium. This makes the positron more than a positively charged version of an electron. It is the electron's antiparticle. Antiparticle does not mean an imitation, a damaged copy, or a particle behaving badly before being removed from the laboratory. It means that the positron occupies the antimatter position corresponding to the electron in the structure of particle physics. The idea of such a particle appeared before anyone had seen one. During the late 1920s, physicists were trying to combine two powerful descriptions of nature. Quantum mechanics was being developed to explain atoms and particles. Special relativity described how space, time, energy, and motion behave at very high speeds. Each theory worked extremely well in its own domain, but bringing them together was difficult. Paul Dirac developed a new description of the electron that respected both quantum mechanics and special relativity. His work successfully included the electron spin, but it also produced unexpected possibilities. The mathematics appeared to require a particle related to the electron, but carrying the opposite electrical charge. At first, this was not a comfortable result. Physicists do not usually celebrate when an equation seems to produce an entire particle that no one has ordered. A new mathematical possibility can mean that nature contains something undiscovered, but it can also mean that the interpretation is wrong. The only reliable way forward is to look. 4 years later, Carl Anderson was studying cosmic rays with a cloud chamber. Cosmic rays are high-energy particles arriving from space. When they strike the atmosphere or pass through matter, they can produce showers of other particles. A cloud chamber makes the paths of charged particles visible as thin trails of condensed droplets. A magnetic field bends those trails. The direction and degree of the bending help reveal the sign of a particle's charge and provide information about its momentum. Anderson recorded a track that curved as though it had positive charge, yet behaved like a particle far lighter than a proton. A lead plate inside the chamber helped him determine the direction in which the particle had travelled. The evidence pointed to a positive particle with a mass close to that of the electron. The positron had moved from mathematical possibility to experimental fact. That discovery changed the meaning of matter. Until then, the known collection of particles seemed to be a small set of ingredients from which the universe had been assembled. The positron showed that at least one familiar particle had an antimatter partner. Later discoveries confirmed that the pattern extended much further. Protons have antiprotons. Neutrons have antineutrons. Other fundamental particles also have corresponding antiparticles, although particles with no electrical charge require a more careful description, because some can be their own antiparticles. For our story, the electron and positron are the essential pair. An ordinary electron is stable. As far as experiments have shown, it does not simply decay while sitting by itself. A positron is also stable when properly isolated. Its reputation for vanishing quickly comes from the fact that our surroundings contain an enormous number of electrons. Every ordinary atom carries electrons. Solids, liquids, gases, dust, laboratory equipment, human bodies, and mildly neglected kitchen surfaces are full of them. A positron moving through ordinary matter therefore has many opportunities to encounter its antimatter partner. This is why antimatter is difficult to store. It cannot be placed in an ordinary container. The walls of the container are made from matter, so contact would lead to annihilation. Laboratories use electric and magnetic fields to confine charged antiparticles without allowing them to touch the apparatus. The positron itself is not impatient. It does not carry a personal countdown that begins as soon as it is created. Its future depends on its environment. In a suitable trap and a very good vacuum, positrons can be held for long periods. Send one into a solid or a gas, and its situation changes completely. A fast positron entering matter interacts electrically with the atoms around it. It can scatter from electrons and nuclei, losing energy as it travels. It may knock electrons into different states or remove them from atoms. Eventually, after enough collisions, the positron slows down. At that stage, several outcomes are possible. It may annihilate with an electron without forming positronium. It may become temporarily associated with an atom or molecule. Under the right conditions, it may capture an electron into the bound partnership we call positronium. The word partnership is useful as long as we do not take it too literally. The particles do not make a decision to cooperate. They are responding to the electromagnetic force and the rules of quantum mechanics. Still, the contrast is worth noticing. The same two particles capable of annihilating can also form an organized atomic system. Their opposite charges create attraction. A negative electron and a positive positron pull toward one another in the same general way that an electron is attracted to the positive nucleus of hydrogen. If their motion and energy fall within the right range, the attraction can keep them together. That does not mean they settle into a fixed distance and remain there like two magnets on a table. Positronium is quantum mechanical. The electron and positron are described by a shared quantum state. Their positions are spread across probability distributions, and the distance between them is not a single permanent value. Pictures often show one particle circling the other. This is convenient, but it can be misleading. In positronium, neither particle acts as a stationary centre. They have equal mass, so both respond equally to their mutual attraction. The useful centre is the centre of mass, located halfway between them when they are considered at opposite positions. Hydrogen behaves differently because the proton is much heavier than the electron. The proton also moves, but its motion is small compared with that of the electron. In many simple descriptions, it is reasonable to treat the proton as nearly fixed. No such shortcut works for positronium. The electron and positron share the motion evenly. Each moves around their common centre. This equal arrangement is one reason positronium has energy levels different from those of hydrogen, even though both systems involve one negative particle attracted to one positive particle. The two charges cancel when the system is viewed as a whole. Positronium is electrically neutral. From far enough away, its positive and negative charges balance. Up close, however, the separate charges still matter. External electric and magnetic fields can influence the atom, and collisions with surrounding particles can disturb it. Neutral does not mean invisible to everything. A neutral cat can still knock a glass off a table, and a neutral atom can still interact with its surroundings. Positronium is especially delicate because it is light, short-lived, and made from two particles that can annihilate. This brings us to the most common puzzle. If the electron and positron attract each other, and if they annihilate when they meet, why does positronium last at all? The question comes from picturing annihilation as a mechanical event. Two hard objects travel along definite paths, collide, and disappear at the instant their surfaces touch. Quantum particles do not behave that way. An electron does not have a known solid surface, neither does a positron. They are described through quantum fields and probability states. Their annihilation is an allowed interaction, but allowed does not mean immediate. Quantum theory assigns a rate to the process. For annihilation to occur, the electron and positron must have sufficient overlap in their quantum state, and the final products must satisfy conservation laws. Energy must be conserved, momentum must be conserved, electrical charge must be conserved. Angular momentum and other relevant quantum properties must also balance. Nature is flexible about what may happen, but very strict about the bookkeeping. Before annihilation, the total electrical charge of the pair is zero because the negative and positive charges cancel. After annihilation, the light particles that are usually produced also carry no electrical charge. The energy associated with the particle's mass and motion has not been destroyed. It has changed form. The phrase matter is converted into energy is often used here, but it can create a false division. Matter already possesses energy. The mass of the electron and positron is one part of the total energy of the system. During annihilation, that energy is transferred into other particles, usually particles of light. Nothing has been removed from the accounting. The electron and positron are gone, but their energy and momentum remain in the products. While positronium exists, annihilation is possible at every moment. It is not guaranteed at a precisely scheduled instant. Each atom has a probability of decaying during a particular interval. Across a large collection, the average lifetime is predictable. The situation resembles radioactive decay. Scientists can accurately describe how a large group will decrease over time, yet they cannot point to one atom and announce the exact instant when it will vanish. Positronium is governed by the same kind of statistical certainty. The internal state makes an enormous difference. The spins of the electron and positron can combine in two main arrangements. One arrangement allows a faster route to annihilation. The other is restricted by the conservation rules and usually lasts much longer. We will examine those forms separately later because the distinction explains much of positronium's behaviour. At this stage, the important point is that annihilation is controlled by quantum state. It is not merely the result of two opposite particles being nearby. This is also why an electron and positron can scatter without annihilating. They may approach, interact electrically, and move apart again. Annihilation is one possible result, not the only result. Imagine two people entering the same railway station. They might pass each other, stop for a conversation, board the same train for a short distance, or leave through different exits. The analogy has limits, especially because railway passengers do not usually transform into light, but it reminds us that an encounter does not dictate a single outcome. The quantum version depends on energy, motion, spin, and the surrounding environment. When the electron and positron become bound, their combined energy is slightly lower than it would be if they were free and far apart. That difference is the binding energy. To create the bound state, the system must dispose of excess energy and momentum in some way. This requirement is easy to overlook. Attraction alone is not always enough to make a lasting bound object. If two particles rush toward one another with too much energy, they may simply scatter. To settle into a bound state, something must carry away the extra energy. In different formation processes, that task can be handled by another particle, an atom, a molecule, or emitted radiation. The details depend on how the positronium is produced. This is why certain materials are good positronium converters while others are not. Once formed, the pair has an atomic structure. It can occupy a lowest energy state or one of several excited states. An excited positronium atom contains more internal energy. It can move to a lower state by emitting light, just as ordinary atoms do. Here again, the matter and antimatter partnership behaves less like a brief collision and more like an atom. Positronium has a spectrum. It can interact with laser light. Researchers can use carefully chosen light to move it between states, slow its motion, or prepare it for further experiments. The atom may be temporary, but it is not crude. Its internal behaviour is detailed and measurable. Because the electron and positron have equal mass, positronium is extremely light compared with ordinary atoms. Even hydrogen, the lightest chemical element, is far heavier because its proton contains much more mass than an electron. That low mass affects how positronium moves. At a given temperature, a light particle tends to move faster than a heavy one. A newly formed group of positronium atoms can therefore spread quickly, making them difficult to control before annihilation. Researchers have developed techniques to produce positronium in vacuum, excite it with lasers, and reduce its range of velocities. These efforts are technically demanding because the experiment must act during the atom's short lifetime. The equipment needs to deliver positrons, form positronium, apply light at the correct moment, and detect what happens next. There is little room for a slow start or a machine that needs to restart itself at an inconvenient time. The attraction between electron and positron also reveals an important point about antimatter. Antimatter does not automatically repel matter. Electrical behaviour depends on charge, not on the labels matter and antimatter. A positron is positively charged, so it's attracted to a negatively charged electron and repelled by a positively charged proton. An antiproton is negatively charged, so it is attracted to a positron. That pairing produces antihydrogen, an antimatter atom made from an antiproton and a positron. Matter and antimatter are not two substances governed by opposite versions of every force. They are categories of particles related by deep symmetries. Their interactions still follow the same physical laws. Gravity presents a separate experimental question, especially for neutral antimatter systems such as antihydrogen. Positronium is more complicated as a gravity test because it lives briefly and moves rapidly. Even so, researchers are interested in whether its motion might eventually help test how systems containing equal amounts of matter and antimatter respond to gravity. No accepted experiment has shown that antimatter falls upward. That popular idea is not part of established physics. Current evidence from antihydrogen is consistent with downward gravitational motion, although increasingly precise measurements remain scientifically valuable. For positronium, the immediate partnership is ruled mainly by electromagnetism. The opposite charges pull together far more strongly than gravity affects these tiny particles in a laboratory. The symmetry of the pair makes positronium especially clean. In an ordinary atom, the nucleus has structure. A proton is not fundamental. It contains quarks and gluons, and its size and internal behavior can influence very precise measurements. Electrons and positrons, by contrast, are treated as point-like fundamental particles in the Standard Model. Experiments have not revealed any smaller components inside them. A positronium atom therefore avoids the uncertainties associated with nuclear size and nuclear structure. The simplicity is not complete. The pair interacts through quantum fields. Temporary processes can occur in which particles are emitted and reabsorbed. Annihilation can contribute to energy shift even before the final decay. Relativistic effects matter when predictions become precise. Still, there are only two constituents, and they are matched in mass. That makes positronium one of the best places to test the theory of electromagnetic interactions at high precision. Any measurement begins with a real partnership, not merely a theoretical diagram. A positron must be created, slowed, and brought into an environment containing electrons. One of those encounters must lose the right amount of energy. The resulting positronium must survive long enough for a detector or laser to act. This creates an interesting balance. The electron and positron attract because their charges are opposite. They annihilate because they are particle and antiparticle. Their attraction brings them into the overlap needed for annihilation, yet the quantum state can preserve the bound system for a measurable interval. The partnership is therefore neither stable nor instantaneous. It occupies the narrow region between scattering and destruction. That region is wide enough for atomic physics. During it, the particles share a center, occupy energy states, respond to fields, and reveal the orientation of their spins. Their eventual annihilation provides the signal that allows researchers to know the atom existed. In many experiments, scientists never watch positronium directly in the ordinary sense. They infer its presence from timing, radiation, and the way those signals change under controlled conditions. The atom announces itself mainly by disappearing. Before it can make that announcement, however, several practical events must occur in the correct order. The positron begins with too much speed. Matter slows it. An electron becomes available. Excess energy is removed. Only then can the temporary atom take shape. Following that sequence brings us from the general relationship between matter and antimatter to the specific process that creates positronium, which begins not with annihilation, but with a positron entering ordinary matter and gradually losing the energy that once kept it free. A positronium atom begins with a positron that is moving too quickly to become part of anything. Positrons are often born with a considerable amount of energy. Some come from radioactive nuclei. Others are produced when energetic particles strike a target and create new particle pairs. In either case, the newly created positron is usually travelling far too fast to settle into a bound state with an electron. It must first slow down. That sounds simple, but the slowing process is one of the most important stages in the formation of positronium. A fast positron entering matter does not glide gently to a halt like a bicycle approaching a quiet junction. It passes through a dense collection of atoms and interacts with the charged particles inside them. The nuclei carry positive charge, so they tend to repel the positron. The electrons carry negative charge, so they attract it. As the positron moves through the material, these electrical interactions repeatedly change its direction and reduce its energy. Some encounters are gentle. The positron passes an atom, transfers a small amount of energy, and continues on a slightly altered path. Other encounters are more disruptive. The positron may excite an electron inside an atom or molecule, raising it to a higher energy state. It may also knock an electron completely free, leaving behind a positively charged ion. Each interaction removes part of the positron's original motion. The path is not a smooth line. It becomes a complicated trail of collisions, ionized atoms, displaced electrons, and small regions of disturbed material. By the time the positron has slowed substantially, it may have created many of the electrons that could later take part in forming positronium. This is especially important in liquids and solids. A fast positron does not merely arrive in a material and select a convenient electron from a neatly arranged shelf. Its passage changes the local environment. It leaves behind a track containing ions and free or partly free electrons. Near the end of that track, the positron has less energy and changes direction more frequently. Its motion becomes less like a projectile and more like a wandering particle being jostled by the material around it. Researchers sometimes describe the final region of this track as a small cluster of ionization. It contains the slowed positron, several positive ions, and a collection of electrons that have been separated from their original atoms or molecules. The scene is crowded, electrically active, and extremely brief. There is also a small practical difficulty. The positron is positively charged, while the ions it has created are positive as well. Those ions tend to repel it. The freed electrons, however, are negative and are attracted to the positron. The result is competition. The positron may move away from the region. It may encounter an electron and annihilate directly. It may become trapped by some feature of the material, or it may capture an electron and form positronium. The word capture can make the process sound as though the positron reaches out and grabs an electron. What actually happens is a change in the quantum state of the particles. Before formation, the positron and electron belong to separate states in the material. After formation, they share a bound state. For that change to occur, the energy must be right. A free electron and a free positron approaching one another cannot always become positronium by themselves. A bound positronium atom has less energy than the same two particles when they are separated. The excess energy must go somewhere. Energy does not quietly disappear because two particles have found each other agreeable. Another object must carry some of it away. That object may be an atom, a molecule, a surface, another particle, or a particle of light. The formation mechanism depends on the environment. Consider a positron colliding with an isolated atom in a gas. The atom already contains electrons bound to its nucleus. If the incoming positron has enough energy, it can take one of those electrons. The electron leaves the original atom and joins the positron. The original atom is left positively charged, while the electron and positron depart together as positronium. This process is known as charge exchange. The name is slightly misleading because no one passes a small parcel of charge across a counter. It simply describes the rearrangement. The electron was originally bound to the atom. After the collision, it is bound to the positron. The collision can produce positronium in its lowest energy state or in an excited state. The result depends on the speed of the incoming positron, the type of target atom or molecule, and the details of the interaction. Not every collision succeeds. The positron may scatter and leave the atom unchanged. It may excite or ionize the target without taking an electron. It may annihilate with one of the electrons. Quantum physics assigns probabilities to these different outcomes. There is also an energy threshold. The positron must bring enough energy to remove the electron from its original atom, but the binding gained when positronium forms helps to pay part of that cost. Atoms hold their electrons with different strengths. An electron that is weakly bound can be transferred more easily than one held tightly. As a result, the amount of incoming energy needed for positronium formation varies from one target to another. Once the process becomes energetically possible, its probability does not simply rise in a perfectly smooth and predictable manner. The internal structure of the target matters. Different energy states become available. Quantum interference can enhance one outcome and suppress another. This makes positron scattering a rich field of study in its own right. A beam of positrons passing through a gas can reveal how readily different atoms and molecules form positronium. The resulting measurements also test calculations of collisions involving several interacting particles. In a solid, the formation story is different because the electrons belong to a closely packed material rather than isolated atoms. A positron entering a solid usually penetrates beneath the surface. How deeply it travels depends on its initial energy and the density of the material. As it slows down, it loses energy through repeated interactions with electrons and atoms. After slowing, the positron may diffuse through the solid for a short distance. It can become trapped at a defect, such as a missing atom in a crystal structure. It can annihilate directly with an electron. In suitable materials, it can form positronium. Dense metals are not always helpful places for positronium to survive. Their many mobile electrons make direct annihilation likely, and the structure of the material may not provide enough space for the newly formed atom. Insulating materials and porous substances can be much better. Silica is a widely used example. It can be prepared with a network of tiny pores and channels. When positrons are directed into nanoporous silica, some of them capture electrons and become positronium inside the material. The positronium may then move through the pores. In some designs, it reaches the surface and escapes into the surrounding vacuum. This provides researchers with a source of positronium atoms that can be studied without constant collisions with the material. The target therefore performs several jobs. It slows the incoming positron, it provides an electron, it absorbs excess energy and momentum during formation. Its pores give the positronium room to move. Finally, its surface allows some of the atoms to emerge into vacuum. That is an impressive amount of assistance from something that looks, from the outside, like a thin and rather unexciting film. The internal pore structure is crucial. Pores that are too small can confine the positronium strongly or increase its interactions with the walls. Pores that are connected may allow the atom to travel toward the surface. Temperature also matters because it influences how positronium moves through the material and how much energy it carries when it escapes. The surface chemistry can change the result as well. Atoms or molecules attached to the pore walls may interact with positronium. Defects can trap positrons before formation or alter the probability of an electron being captured. Producing a useful beam therefore requires careful material design. Researchers do not simply purchase a bag marked antimatter atom maker and pour it into the apparatus. They study pore sizes, coatings, implantation energies, temperatures, and emission directions. Some experiments begin with radioactive positron sources. A radioactive isotope releases positrons over time, and surrounding equipment guides or moderates them into a slower beam. A moderator is a material used to reduce the energy spread of the positrons. Fast positrons enter it, lose energy, and a small fraction return from the surface with much lower energies. Electric and magnetic fields can then collect and guide them. Other facilities produce positrons using particle accelerators. A beam of energetic electrons strikes a dense target. The collisions generate radiation, and that radiation can produce electron and positron pairs. The positrons are separated, slowed, and collected. Neither method produces a tidy queue immediately. The positrons begin with a broad range of energies and directions. Building a controlled source requires several stages of selection, slowing, transport, and storage. Positrons can be accumulated in electromagnetic traps. These devices use electric potentials and magnetic fields to keep the charged particles away from ordinary matter. A gas may be introduced to help the positrons lose energy without disappearing too quickly. The trapped positrons can then be released as a short pulse. That pulse strikes a positronium-producing target, often within a very narrow time window. A pulsed source is useful because researchers know when the positrons arrived. Detectors can measure the delay between implantation and annihilation. Lasers can be fired at the moment when the positronium atoms are expected to emerge. Timing is essential. The atom does not remain available while the research team checks whether everyone is ready. In a modern experiment, electronic triggers coordinate the positron pulse, the laser system, and the detectors. A delay that would seem negligible in everyday life can determine whether the laser interacts with the newly formed atoms or arrives after they have annihilated. The atoms leaving a porous target are not all identical. They can have different speeds and travel in different directions. Some remain inside the material, some collide with pore walls, some emerge into the vacuum. Even those that escape may carry more motion than the experiment would prefer. A fast positronium atom crosses the apparatus quickly, leaving less time for observation. Its motion can also broaden the frequencies at which it absorbs light. Researchers therefore try to cool positronium. Cooling does not necessarily mean placing it beside a small refrigerator. It means reducing the random motion of the atoms. The target material can help by allowing positronium to collide with pore walls and lose energy before emission. Laser light can also be used to change the motion of selected atoms. The difficulty is that the cooling must happen before annihilation. Ordinary atoms may be trapped and cooled over long periods. Positronium gives the experiment only a tiny interval in which to act. This has encouraged the use of excited states with longer effective lifetimes. When positronium absorbs light, one of its possible changes is a transition to a higher energy state. In some highly excited states, the electron and positron are typically farther apart. Their quantum states overlap less strongly, reducing the likelihood of immediate annihilation. These enlarged states are often called Rydberg states. They can survive long enough for the atom to travel farther and respond strongly to electric fields. Researchers can use those fields to guide or manipulate the excited positronium. The atom is still temporary, but exciting it can provide valuable extra time. Formation in gases offers another way to prepare excited positronium. A positron beam passes through a cell containing a carefully chosen gas. Through charge exchange, the positron takes an electron from a gas atom or molecule. Under suitable conditions, many of the resulting positronium atoms occupy particular excited states. This can produce a beam travelling in a fairly well-defined direction, because the original positron already had controlled motion. The price is that the surrounding gas can cause additional collisions, and the formation efficiency depends sensitively on the beam energy. There are also methods involving interactions between positrons and prepared electrons, but bringing two free particles together and creating a bound atom is not easy. Something still has to carry away the binding energy and momentum. One possibility is radiative formation, in which the electron and positron bind while emitting a particle of light. This process is allowed, but under many laboratory conditions it is less efficient than formation involving a material, a gas target, or a surface. A third particle can assist as well. It can absorb energy and momentum, allowing the electron and positron to remain bound. In dense environments, the surrounding matter naturally provides many possible participants. Liquids present their own version of the process. A positron released inside a liquid creates a trail of ionization as it slows. Near the end of the trail, the positron may encounter one of the electrons it has displaced. The electron and positron can form an initial loosely associated state before the surrounding liquid adjusts around them. The liquid molecules do not ignore the new atom. Their electrons and charges respond to it. Positronium tends to push surrounding molecules away because its electron experiences repulsion from the electrons in those molecules. This can create a tiny region of additional free space, often described as a bubble. The bubble is not a hollow sphere with a sharp wall. It is a nanoscale rearrangement of the liquid. The positronium occupies the lower density region, while the surrounding molecules are kept at a slightly greater distance. The size of this region and the interactions at its boundary influence the lifetime of the atom. An electron from a nearby molecule can annihilate with the positron inside positronium. Chemical substances dissolved in the liquid can also react with the atom or change its internal spin state. This is why positronium formation and decay are sensitive to the local environment. The atom is not only born from the material, it immediately begins reporting information about it through the way it behaves. Oxygen is particularly effective at influencing positronium in many substances. Other molecules can reduce its lifetime or suppress its formation. Temperature and pressure alter the available free space and the motion of surrounding molecules. In biological tissue, the situation is even more complicated. Water, proteins, membranes, dissolved gases, and many chemical compounds create a varied environment. Some positrons form positronium, while others annihilate directly. Measuring the lifetime distribution can reveal differences in the microscopic spaces and chemical conditions within the tissue. That possibility is one reason researchers are investigating positronium as an additional source of information in medical imaging. Whatever the environment, the birth of positronium is never entirely separate from its surroundings. The positron arrives with a history. It was produced by a nuclear decay or a high-energy collision. It was guided, slowed, or scattered. It entered a gas, liquid, solid, or prepared surface. It encountered electrons whose own states were determined by the material around them. Formation occurs only when the particles reach the right combination of energy, position, and quantum state. The surrounding system must accept whatever energy and momentum the new atom can no longer carry as free particles. Then the electron and positron become one bound object. No visible flash marks the exact moment of formation. The stronger signal usually comes later, when the atom annihilates. Researchers infer the birth from what follows. A delayed annihilation suggests that positronium existed between the positron's arrival and the detected radiation. The directions and energies of the outgoing particles provide additional information. Laser-induced changes can confirm that the atoms occupied particular energy states. Repeated many times, these signals reveal how efficiently a target produces positronium, how quickly the atoms leave it, how fast they move, and which internal states were formed. Not every positron creates positronium. Many annihilate directly. Others become trapped or lost. The fraction that succeeds depends on the formation method and the material. That limitation is one of the central challenges in positronium research. Fundamental experiments often need large numbers of atoms. Each stage loses particles. Only some produced positrons are captured. Only some trapped positrons reach the target. Only some form positronium. Only some escape into vacuum. Only some interact with the laser or detector in the required way. A laboratory may begin with a powerful source and finish with a much smaller group of useful atoms. Improving that chain requires better positron accumulators, more efficient converters, colder emission, stronger laser control, and detectors capable of distinguishing the desired events from background signals. The reward is a source of neutral matter and antimatter atoms that can be directed into experiments. Because positronium has no overall electrical charge, ordinary electric fields cannot steer its ground state as easily as they steer a free positron. Excited positronium is more responsive, allowing researchers to manipulate it through its internal electric properties. Neutrality is helpful for some measurements because the atom is less affected by stray electric fields. It is inconvenient when someone wishes to make it turn left. These practical concerns explain why so much research focuses on the moment of birth. Producing positronium is not merely the first step before the interesting physics. The production process determines the atom's speed, direction, internal state, and surrounding environment. Those properties influence every measurement that comes afterward. An atom created inside a liquid behaves differently from one emitted into vacuum. An atom formed in its lowest energy state offers different possibilities from one prepared in an excited state. A warm, rapidly moving cloud presents different experimental challenges from a cold, directed beam. Yet each begins with the same basic rearrangement. A positron loses enough energy to approach an electron under suitable conditions. Their opposite charges provide the attraction. The environment removes the excess energy and momentum. Two separate particles become a shared quantum system. Once that system exists, even briefly, it must be described as more than an electron beside a positron. It has its own energy levels, size, motion, and internal states. Its two constituents no longer orbit a heavy central particle, because there is no proton, neutron or nucleus waiting in the middle. Both particles move. Both contribute equally. The centre of the atom contains no material object at all, and understanding that empty centre is the next step in seeing what positronium really is. Once the electron and positron have released enough energy to remain together, the result is an atom that does not fit the usual picture of an atom. There is no proton at its centre. There are no neutrons packed beside that proton. There is no dense nucleus carrying almost all the mass, while a much lighter electron occupies the surrounding space. Positronium contains only two particles, an electron and a positron, and both of them move. This makes it an exotic atom rather than a chemical element. Chemical elements are identified by the number of protons in their nuclei. Hydrogen has 1 proton, helium has 2, carbon has 6. Positronium has none, so it has no place on the periodic table. Calling it an atom is still useful because it behaves like one in several important ways. Its particles are held together by electrical attraction. It has a lowest energy state and a series of excited states. It can absorb light, release light, and move between those states at specific frequencies. It can travel as a neutral object and collide with other atoms and molecules. The missing nucleus does not prevent atomic behaviour. It simply changes who takes part in that behaviour. In ordinary hydrogen, the positively charged proton is much heavier than the negatively charged electron. The proton is not completely motionless, but because of its much greater mass, it moves only a little compared with the electron. A basic description can place the proton near the centre and treat the electron as the main moving particle. That shortcut is so familiar that it shapes the way many people picture every atom. There is something heavy in the middle and something light moving around it. Positronium removes that arrangement entirely. The positron has exactly the same mass as the electron. When they attract each other, neither one can serve as a fixed centre. Each accelerates toward the other by the same amount. Each contributes equally to the internal motion of the atom. The point around which they move is their shared centre of mass. For two particles with equal mass, that point lies halfway between them. It is a useful mathematical location, but there is no object sitting there. The centre of positronium is empty. This does not mean the atom contains a permanent hollow space with a clear boundary. Quantum particles do not remain on opposite sides of a little vacant room. The statement simply means that there is no central particle acting as a nucleus. The electron and positron are both distributed through a shared quantum state around their common centre. At one moment, a measurement might find the electron on one side and the positron on the other. A later measurement on another identically prepared atom could produce a different arrangement. Before measurement, quantum mechanics does not assign them two exact paths that can be followed like vehicles on a roundabout. The common illustration of two particles circling one another can be helpful, but only if it is treated as a rough guide. It shows that both particles move and that neither occupies the centre. It should not be mistaken for a photograph of what they are literally doing. A more accurate description uses a probability distribution. This distribution tells physicists how likely the particles are to be found at different separations and locations. In the lowest energy state, they are most likely to remain relatively close. In excited states, the average distance between them becomes greater. The exact position of the whole atom is a separate matter from the internal distance between its two particles. A positronium atom can travel across a laboratory, while the electron and positron continue their internal motion around the shared centre. Physicists can describe the movement of that centre through space, and they can describe the movement of the particles relative to each other. Keeping those two types of motion separate makes the system easier to understand. The first type is the motion of positronium as a complete object. It may leave a porous material, cross a vacuum chamber, pass through a laser beam, or collide with a surface. The second type is the internal motion that holds the atom together. The electron and positron continually respond to their mutual electrical attraction while occupying the quantum state of the atom. This separation is possible because both particles contribute to the total motion in a predictable way. Their equal masses make the arrangement unusually balanced. It also changes the strength and scale of the atom compared with hydrogen. In hydrogen, the heavy proton hardly shifts while the electron responds to the attraction. In positronium, the electron and positron both move. The effect is similar to replacing a fixed anchor with another object that is equally free to move. As a result, positronium in its lowest energy state is larger than hydrogen in its lowest energy state. Its typical electron to positron separation is about twice the corresponding scale in hydrogen. It is also less tightly bound. The energy required to separate the electron and positron is about half the energy required to remove the electron from an ordinary hydrogen atom in its lowest state. This weaker binding does not mean positronium is about to fall apart on its own. If it were made from two ordinary particles that could not annihilate, electrical attraction would still provide a genuine bound state. The problem is not that the bond is too weak. The problem is that the two particles are allowed to annihilate. That distinction matters. Positronium does not disappear because the electron escapes from the positron. In its usual decay, the bound state ends because the electron and positron are converted into other particles. The atom does not slowly loosen until its pieces drift away. Its constituents cease to exist as an electron and positron. Before that occurs, the attraction between them produces an entire set of allowed energy states. Quantum mechanics does not allow a bound atom to possess any internal energy it pleases. Only particular states are available. An electron in hydrogen cannot occupy a position halfway between two allowed energy levels. Positronium follows the same general rule. The lowest allowed state is called the ground state. It is the state with the least internal energy. Above it are excited states, each with a different distribution of motion and a different typical separation between the particles. A positronium atom can enter an excited state when it receives energy, often by absorbing light. It can move to a lower state by releasing energy, which may also appear as light. The light must have the correct frequency for the transition. Too little energy will not move the atom to the desired state. Too much may send it somewhere else, or separate the electron and positron completely. This selective response is the basis of spectroscopy. Researchers expose positronium to carefully controlled radiation and observe when the atom reacts. By measuring the required frequencies, they determine the differences between its energy levels. These measurements provide much more than a catalogue of atomic behaviour. The positions of the energy levels are predicted by the theory of electromagnetic interactions. A precise comparison between prediction and experiment can reveal whether every known effect has been included correctly. Positronium is especially useful because it has no nucleus. In hydrogen, extremely precise calculations must account for the proton. Although the proton is often drawn as a simple dot, it has an internal structure. It is made from quarks and gluons. Its charge is spread across a small but measurable region. Its magnetic properties and internal motion affect the energy levels of the atom. Those effects are fascinating, but they can complicate a test of the interaction between the electron and the electromagnetic field. A disagreement between theory and experiment may come from the electron, the proton, the interaction between them, or an imperfect understanding of proton structure. Positronium removes the proton from the calculation. Both of its constituents belong to the group of particles called leptons. As far as experiments can determine, the electron and positron have no smaller components. They are treated as fundamental point-like particles in the standard model. For this reason, positronium is often described as a purely leptonic atom. Its behaviour does not depend on the uncertain internal structure of a nucleus. That makes it a particularly direct testing ground for quantum electrodynamics, the theory that describes interactions between charged particles and light. The theory must still account for many subtle effects. The electron and positron interact by exchanging the influence of the electromagnetic field. In the simplest picture, their opposite charges attract. More precise calculations include additional quantum processes. The particles can interact through temporary disturbances in the field. The surrounding vacuum can affect them. Their motion must be corrected for the effects of special relativity. There are also processes connected to annihilation even while the atom still exists. Quantum theory allows the electron and positron to enter a temporary intermediate state related to annihilation, and then return to the bound system. These virtual processes do not produce the final destruction of the atom, but they can shift its energy levels by a very small amount. That may sound like nature briefly starts the annihilation, changes its mind and puts everything back. The proper quantum description is less personal, but the calculation really does have to include possible intermediate interactions that cannot be observed as separate events. Such effects are tiny. Modern spectroscopy is precise enough that tiny effects matter. A measurement can focus on the difference between two energy states and determine it with extraordinary accuracy. The experimental result is then compared with calculations containing many layers of corrections. If the two disagree, researchers first examine the ordinary explanations. The laser frequency may need better calibration. The positronium atoms may be moving, causing a shift in the light they absorb. Electric or magnetic fields may be disturbing the states. Collisions with the target or residual gas may be influencing the measurement. Only after these possibilities are understood can anyone reasonably ask whether the disagreement points to missing physics. This careful process is one reason positronium experiments can take years. The atom may be simple, but the laboratory around it is not. A moving atom sees the frequency of incoming light shifted according to its speed and direction. If the positronium atoms leave a target with many different velocities, the transition can appear broadened. Cooling the atoms and controlling their motion can improve the measurement. The atom's short lifetime creates another difficulty. A laser must act before annihilation. Detectors must distinguish the desired response from the signals produced by positrons that never formed positronium. Surfaces and electric fields must be controlled without blocking the atoms or destroying them. The absence of a nucleus therefore makes the theory cleaner, but it does not make the experiment effortless. It also gives positronium a different relationship with external fields. The total electric charge of the atom is zero. The negative charge of the electron and the positive charge of the positron cancel. A uniform electric field does not simply pull the whole atom in one direction, as it would pull a free charged particle. The separate charges can still respond within the atom. An external field may pull the electron slightly one way, and the positron slightly the other way. This distorts the shared quantum state and shifts its energy. The effect becomes much stronger in highly excited positronium. In those states, the particles are typically farther apart, so the atom is easier to distort. Researchers can use changing electric fields to influence the motion of these excited atoms. Magnetic fields also matter, because both the electron and positron have magnetic properties connected to their spin. A field can shift energy levels, mix certain states, and change the observed annihilation behavior. This sensitivity gives scientists useful control, but it also means unwanted fields must be carefully measured. A small magnetic field from nearby equipment can become important when the experiment is trying to determine an extremely small difference between energy levels. The structure without a nucleus influences collisions as well. Ordinary atoms present an electron cloud surrounding a compact positive center. Positronium presents a positive and negative particle with equal freedom to move. When it approaches another atom or molecule, both of its charges respond to the surrounding electrons and nucleus. The positron can be repelled by a positive nucleus and attracted to the target's electrons. The electron inside positronium is attracted to the nucleus and repelled by the other electrons. These competing interactions can scatter the atom, break it apart, change its internal state, or lead to annihilation. In a material, the positron may annihilate with an electron that did not originally belong to the positronium atom. This process is often called pick-off annihilation because the positron effectively annihilates with an outside electron, while its original partner remains behind. The probability of this happening depends on how much the positronium state overlaps with the electrons in the surrounding material. In a large empty pore, the atom may spend more time away from the walls and survive longer. In a smaller space, interactions with the walls become more frequent, and the measured lifetime can decrease. This turns the atom's delicate structure into a measuring tool. Since positronium has no solid nucleus, its size is determined entirely by the probability distribution of the electron and positron. That distribution responds to confinement. Place the atom in a small cavity, and the available space alters its motion and energy. By studying its lifetime and energy changes, researchers can infer the size and properties of microscopic, empty regions in solids and liquids. The atom becomes a probe that is itself mostly open space, examining spaces that are too small for ordinary imaging methods. Excited positronium shows the same nucleus-free structure on a much larger scale. When the atom absorbs enough energy without becoming ionized, it can enter a state in which the typical separation between the electron and positron is greatly increased. These states are often called Rydberg states. The higher the excitation, the larger and more weakly bound the atom becomes. In very highly excited states, the electron and positron can be separated by distances enormous compared with the size of the ground state, although still tiny by everyday standards. The overlap between the two particles may then decrease. Since annihilation depends partly on their quantum overlap, certain excited states can survive longer than the ordinary ground state. Researchers use this extra lifetime to manipulate positronium and send it toward other parts of an experiment. An excited atom can travel farther before disappearing. Its strong response to electric fields makes it easier to guide. There is a trade-off. Highly excited positronium is fragile. A modest electric field may separate the particles. Collisions can disturb it. Thermal radiation from the surroundings can drive transitions. Preparing and controlling it requires careful timing. Still, the ability to enlarge the atom shows how complete its atomic structure really is. Positronium is not merely an electron and positron waiting in the same location. It has a full sequence of states extending from a compact ground state to enormous excited configurations. The lack of a nucleus also creates a perfect symmetry between its two constituents. In hydrogen, the electron and proton have different masses, different internal properties, and different roles in the atom. In positronium, exchanging the positions of the electron and positron leaves the mass arrangement unchanged. Their electrical charges reverse, but the structure remains balanced. This symmetry affects the classification of the atom's quantum states. Physicists must consider how the total state behaves when matter and antimatter are exchanged. They must also account for the relative motion of the particles and the way their intrinsic spins combine. Spin becomes especially important because the electron and positron each carry the same amount of it. Their spins can point in arrangements that combine differently. In one broad arrangement, the two spins oppose each other so that their contributions cancel. In another, their contributions combine to produce a non-zero total. These are not minor variations. They lead to two forms of positronium with dramatically different lifetimes and different usual patterns of annihilation. The energy difference between those spin arrangements is small compared with the total binding energy, but it can be measured. It arises from magnetic interactions between the electron and positron, along with quantum effects connected to their ability to annihilate. This division is known as the hyperfine structure of the ground state. Ordinary atoms also have hyperfine structure, often produced by interactions between the magnetic properties of the nucleus and the electrons. Positronium has no nucleus, so its version comes directly from the relationship between the electron and positron. That makes the measurement another clean test of theory. There is no uncertain nuclear magnetism to include. The result depends on two matched fundamental particles and the electromagnetic field between them. The two forms are usually called para-positronium and ortho-positronium. The names come from the spin arrangement of the pair, not from different ingredients. Both contain one electron and one positron. Both lack a nucleus. Both can occupy atom-like energy states. What changes is how the two spins combine. That internal difference determines which annihilation routes are permitted by the conservation rules. One form can usually disappear through a simpler process and therefore survives for a much shorter time. The other must follow a less direct route and remains present far longer by comparison. The atom's empty centre has brought us to this distinction naturally. Once there is no nucleus to define the structure, the most important internal labels come from the motion and spin of the two equal partners themselves, and those two possible spin arrangements give positronium its two very different ways of existing. Positronium has two main ways of existing in its lowest energy state, and the difference between them comes from spin. Spin is one of those words in physics that sounds more familiar than it really is. In everyday language, spinning means turning around an axis. A wheel spins, a coin spins, someone in an office chair spins until the room begins to object. The spin of an electron or a positron is not that kind of motion. An electron is not known to be a tiny solid sphere rotating through space. Spin is an intrinsic quantum property. It belongs to the particle in the same basic sense that mass and electrical charge belong to it. A particle carries spin even when it is not travelling around anything, and the amount of spin does not depend on how quickly an imagined surface might be turning. What can change is the orientation of that spin when it is measured along a chosen direction. For an electron or a positron, a measurement gives one of two possible results. These are often described as spin up and spin down. The names do not mean that the particle is physically pointing upward or downward. They simply label the two outcomes relative to the direction selected by the experiment. When an electron and a positron form positronium, their individual spins must be considered together. The combined system can be arranged in two fundamentally different ways. In one arrangement, the two spins combine so that the total spin of the atom is zero. This form is called para-positronium. In the other arrangement, the spins combine to give the atom 1 unit of total spin. This form is called orthopositronium. The names para and ortho are labels inherited from the language physicists use for systems that can exist in different spin arrangements. They do not mean that one is normal and the other is unusual. Both are ordinary possibilities for positronium, although their behaviour is very different. Para-positronium is often introduced by saying that the electron and positron spins point in opposite directions. That is useful as a first picture, but the full quantum state is more subtle. There are two possible opposite arrangements. The electron can be measured one way, while the positron is measured the other way, or their roles can be reversed. Para-positronium is a particular quantum combination of those two possibilities. The important result is that the spin contributions cancel. The complete atom has no net spin. Orthopositronium is commonly described as the form with parallel spins. Two of its possible states fit that picture neatly. Both spins can be aligned one way, or both can be aligned the other way. There is also a third state made from a different combination of the two opposite spin arrangements. That third possibility is one reason the simple parallel and opposite description should not be pushed too far. Quantum spin is not a pair of arrows permanently drawn on two tiny particles. What matters is the total state of the pair. Para-positronium has one spin state of this kind. Orthopositronium has three. This difference leads to a useful statistical expectation. Suppose positronium forms in an environment where the electron and positron spins have no preferred orientation. There are four basic combined spin possibilities available. One belongs to para-positronium, while three belong to orthopositronium. Under ideal unpolarized conditions, about 1/4 of the newly formed atoms are therefore expected to be para-positronium, and about 3/4 are expected to be orthopositronium. Real materials can change those proportions. Chemical interactions, magnetic effects, the formation process, and the availability of electrons with particular spin orientations can all influence the result. Still, the 1:3 ratio is the natural starting point. At first, the difference may sound like a minor internal detail. The atom contains the same two particles either way. Its total electrical charge remains zero. Its mass changes only by a tiny amount associated with the difference in internal energy. Its overall size is nearly the same, yet one form survives more than 1,000 times longer than the other in vacuum. Positronium lasts for an average of about 125 trillionths of a second. Positronium lasts for an average of about 142 billionths of a second. Both intervals are extremely short by human standards, but they are very different on the scale of particle interactions. If the lifetime of Positronium were compared with the brief click of a camera shutter, Positronium would seem to remain available for a surprisingly long session. The reason is not that the electrical attraction is stronger in one form. Both are bound by the same basic electromagnetic interaction. The difference comes from the rules governing annihilation. Annihilation must conserve the total properties of the initial system. Energy must be carried away. Momentum must balance. Angular momentum must be preserved. The quantum symmetry of the initial state must also match the allowed final state. Light particles provide the usual final products. A light particle has no electrical charge, so a collection of them can carry away the energy of an electrically neutral electron and positron pair. The difficult part is deciding how many are allowed for each spin state. Positronium usually annihilates into 2 light particles. Positronium usually annihilates into 3. That extra light particle makes the process less likely to occur during any given instant. The interaction has to produce and coordinate a more complicated final state. As a result, Positronium remains alive much longer. The 2 light particles from Positronium behave in a particularly orderly way when the atom is nearly at rest. Momentum must balance, so the particles leave in almost exactly opposite directions. Each carries approximately half of the available energy. Most of that energy comes from the mass of the electron and positron. Each outgoing light particle therefore carries energy close to 511,000 electron volts, when the original atom has little motion. This value appears frequently in positron physics and medical imaging. It is the characteristic energy associated with the annihilation of an electron and a positron at rest into 2 light particles. If the positronium atom is moving, the energies and directions observed in the laboratory are shifted slightly. Motion in the original system must be included in the final balance. Interactions with surrounding matter can also modify the picture. The basic 2-particle decay remains easy to recognize. Detectors placed around a source often record 2 signals arriving from nearly opposite directions within a narrow interval. Positronium produces a less rigid arrangement. 3 light particles share the available energy and momentum. Their directions lie in a common plane when the original atom is at rest, but the energy is not divided into one fixed amount for each particle. One light particle may carry more while the others carry less. Many combinations are possible as long as the total energy and momentum balance. The resulting energy distribution is continuous. Instead of finding only one characteristic value for every particle, detectors observe a range. This difference allows researchers to distinguish many para and annihilation events. 2 nearly opposite signals with the expected energy suggest the usual para decay, or a direct electron and positron annihilation. 3 signals with energies that add to the total, and directions that balance suggest positronium decaying in vacuum. The word usually is important. Positronium can annihilate into a larger even number of light particles, and positronium can annihilate into a larger odd number. Those routes are allowed, but much rarer. Positronium can produce 4 light particles. Positronium can produce 5. Each additional particle makes the process less likely. The dominant outcomes are therefore 2 for Positronium and 3 for Positronium. The separation between even and odd numbers is connected to a quantum symmetry known as charge conjugation. Charge conjugation describes what happens when every particle in a system is replaced by its antiparticle. An electron becomes a positron, and a positron becomes an electron. For a positronium atom, This operation effectively exchanges its two constituents. The para and ortho states respond differently to that exchange. Para-positronium has one type of charge conjugation symmetry, while ortho-positronium has the opposite type. A state made from a certain number of light particles also has a definite behavior under charge conjugation. An even number matches the para state. An odd number matches the ortho state. As long as charge conjugation symmetry is respected by the electromagnetic interaction, para-positronium decays into an even number of light particles, and ortho-positronium decays into an odd number. This is deeper than a convenient counting rule. It connects the lifetime of an atom to a basic symmetry of particle physics. A two-particle annihilation would be much faster for ortho-positronium, but that route does not match the required symmetry. The atom must use the slower three-particle channel. Para-positronium has access to the simpler two-particle route and disappears rapidly. Nature has not made ortho-positronium stable. It has merely closed the quickest exit. The same principle appears throughout quantum physics. A process may seem possible from the standpoint of energy alone, yet fail because another conserved property does not match. The energy is available. The particles exist. The route is still forbidden. Forbidden is another word that requires care. In physics, a forbidden transition is not always absolutely impossible under every imaginable condition. It often means that the process cannot occur through the dominant interaction while the relevant symmetry is preserved. Weaker interactions may not respect every symmetry in exactly the same way. External fields can mix states. New physics, if it exists, could create rare channels. Experiments therefore search for decays that should be absent or extremely suppressed. A clear observation of ortho-positronium decaying into an even number of light particles under well-controlled conditions could signal that an expected symmetry has been violated. The same is true for para-positronium producing an odd number through an unexplained process. Such searches are difficult because ordinary backgrounds can imitate rare events. A three-particle decay may be recorded incorrectly if one signal is missed. A light particle may scatter inside a detector and create extra signals. Positronium may interact with matter before annihilating. Researchers must reconstruct the timing, positions, energies and directions of the detected particles to decide what most likely happened. The ordinary decays are useful for testing other symmetries as well. In ortho-positronium, the directions and polarizations of three outgoing light particles can be compared with the initial spin direction of the atom. Certain patterns would change if fundamental symmetries were violated. Preparing the initial spin is therefore valuable. A magnetic field can help define a preferred direction. Positrons from some radioactive processes are naturally produced with a degree of spin polarization. Under suitable conditions, part of that polarization can be transferred to the positronium. The final annihilation pattern can then be examined for subtle asymmetries. No convincing violation has been established in these measurements. That negative result is scientifically meaningful. It places limits on how strongly unknown interactions could affect the system. The two forms also have slightly different energies before they decay. The electron and positron possess magnetic properties associated with their spins. The interaction between those magnetic properties depends on how the spins are combined. Additional effects related to possible annihilation states contribute as well. Consequently, para-positronium and ortho-positronium are separated by a small energy gap. This is the ground state hyperfine splitting mentioned earlier. Measuring that gap provides a precise test of quantum electrodynamics. Scientists can apply electromagnetic radiation at a frequency corresponding to the difference between the states. They can also place positronium in a magnetic field which shifts and mixes selected spin states, then observe changes in the annihilation signal. A transition from an ortho state into a para component causes the affected atoms to decay much more quickly. The detector sees an increase in two-particle annihilation events, or a change in the measured lifetime. The measurement is demanding. Magnetic fields must be known accurately. The positronium must form in a controlled region. Collisions and material effects must be modelled. Radiation must reach the atoms during the short time they remain available. The reward is a direct view of the internal spin interaction in an atom with no nucleus. The contrast between para and orthopositronium becomes even more useful in matter, although the clean vacuum lifetimes no longer tell the whole story. Para-positronium already decays so quickly that its environment often has little time to interfere. Its lifetime may change slightly, but it generally remains close to its rapid intrinsic value. Orthopositronium has much more time to encounter its surroundings. In a solid or liquid, 142 billionths of a second is long enough for many collisions at the atomic scale. The positron inside orthopositronium can overlap with an electron belonging to a nearby atom or molecule. If that outside electron has the suitable spin relationship, the positron may annihilate with it instead of waiting for the original three-particle decay. This is pick-off annihilation. The original electron from the positronium remains behind, while the positron disappears with an electron taken from the surrounding material. The usual result is 2 light particles rather than 3. Pick-off can shorten the lifetime of orthopositronium from about 142 billionths of a second in vacuum to only a few billionths of a second in condensed matter. The amount of shortening depends on the environment. If the positronium occupies a relatively large empty space, it spends less time overlapping with the electrons in the walls and may survive longer. In a small cavity, the overlap is greater and pick-off occurs more readily. This dependence is the basis of positronium lifetime measurements used to study pores and defects. The long-lived spin state acts as a timer whose rate is changed by the size of the space around it. Parapositronium is usually too quick for this purpose. It vanishes before it can explore much of its environment. Orthopositronium has enough time to encounter the boundaries and provide information about them. Another process can transform orthopositronium into parapositronium. A collision with a molecule containing an unpaired electron can exchange spin information with the atom. This may convert the long-lived triplet arrangement into the short-lived singlet arrangement. Once that happens, the atom rapidly annihilates through the para route. Oxygen is important because ordinary molecular oxygen has unpaired electron spins. The presence of oxygen can therefore affect the lifetime and spin behavior of positronium in a material or biological environment. Other paramagnetic substances can produce similar effects. Measuring changes in orthopositronium may provide information not only about empty space but also about local chemistry. A magnetic field can mix particular para and ortho components as well. The field interacts with the magnetic moments of the electron and positron. One of the ortho spin states can acquire some para character, increasing its probability of 2-particle decay. The remaining ortho states respond differently. The result is a pattern of shifted energies and altered lifetimes that can be used in precision experiments. This makes the labels para and ortho more than names for 2 isolated boxes. In a perfectly undisturbed atom, the states are distinct. In an external field or during collisions, quantum interactions can connect them. Even then, their identities remain useful because the contrast in decay rate provides a clear experimental signal. A small amount of para character can have a noticeable effect on an otherwise long-lived state. The 3 ortho substates also behave differently when a magnetic field defines a direction. Their energies separate according to how their total spin is oriented relative to the field. Researchers can use this splitting to select populations, identify transitions, and study how the atom responds. The basic system contains only 2 particles, yet it provides enough internal structure for a substantial program of spectroscopy. The different lifetimes also influence which form is most visible in an experiment. Parapositronium may be produced in a significant fraction, but it disappears close to the initial positron signal. Its annihilation can blend with direct annihilation events and other prompt processes. Orthopositronium produces a delayed component. If detectors begin timing when the positron enters a material and stop timing when annihilation radiation arrives, the longer delay stands out. A large collection of events creates a lifetime spectrum. The prompt region contains para-positronium and positrons that annihilate without forming a long-lived state. A later distribution contains orthopositronium events. By fitting the timing pattern, researchers estimate how much positronium formed and how long the orthostate survived in each environment. The analysis must account for detector resolution. An instrument cannot mark the time of every event with perfect precision. Signals separated by extremely small intervals may blur together. Parapositronium is particularly challenging because its entire average lifetime is comparable to the timing resolution of many systems. Orthopositronium is easier to separate in time, especially in vacuum. In matter, its shortened lifetime may overlap with other components, requiring careful statistical analysis. The different decay patterns provide additional help. 2-particle and 3-particle events distribute their energy differently. A detector capable of measuring several particles and reconstructing their directions can use both timing and geometry. Medical imaging usually relies on the two nearly opposite light particles produced when a positron annihilates with an electron. Orthopositronium in tissue often undergoes pickoff, which also produces 2 particles. The time between positron emission and annihilation may still contain information about the tissue. Newer experimental approaches aim to measure this lifetime more directly. The goal is not merely to find where annihilation occurred, but to learn something about the microscopic environment in which positronium briefly existed. The para and ortho distinction is essential to that effort. Without the long-lived ortho form, there would be far less time for the atom to respond to pores, molecules, oxygen, and local structure. The short-lived para form remains important for fundamental tests. Its rapid 2-particle decay offers a clean system for comparing measured rates with theoretical predictions. Rare deviations could reveal overlooked effects or place limits on interactions beyond the current theory. Both forms therefore contribute in different ways. Parapositronium gives physicists the simplest dominant annihilation route. Orthopositronium provides a longer observation window, a richer 3-particle final state, and greater sensitivity to the environment. Their ingredients are identical, only the combined spin state changes. That change determines the symmetry of the atom, the usual number of outgoing light particles, the average lifetime, the response to magnetic fields, and the way the atom behaves inside matter. This is one of the clearest demonstrations that quantum information is not merely an added description placed on top of physical reality. The spin state changes what the atom is allowed to do. An observer looking only at the electron and positron count would see no difference. 1 particle of matter and 1 of antimatter are present in both cases. The electrical attraction is present in both. The same total rest energy is available to within the small hyperfine difference. The future of the atom is nevertheless transformed by the way the 2 spins combine. A para-atom is likely to disappear almost immediately into 2 matched light particles. An orthoatom must wait for the less probable 3-particle process unless its surroundings provide a quicker route. To understand what happens during those final instants, it is necessary to move beyond the lifetime and look directly at annihilation itself, including how mass becomes outgoing radiation, how momentum determines the directions, and why the atom's disappearance still obeys exact conservation rules. Annihilation begins when the quantum states of the electron and positron overlap in a way that allows them to stop existing as those 2 particles and produce a different set of particles in their place. This is not a collision between 2 solid objects. There are no tiny surfaces that touch, crack, and release something stored inside. The electron and positron are excitations of quantum fields, and annihilation is an interaction in which those excitations are replaced by new ones. For low-energy positronium, the usual products are photons. Photons are the particles associated with the electromagnetic field. Ordinary visible light is made from photons, but the photons released by positronium carry far more energy than the photons reaching our eyes from a lamp or a screen. They belong to the gamma-ray region of the electromagnetic spectrum. The word annihilation can suggest that something has been reduced to nothing. That is not what happens. The electron disappears. The positron disappears. Their mass, internal energy and motion do not disappear. All of that must be carried away by the particles created in the interaction. Energy remains conserved, momentum remains conserved, electrical charge remains conserved, angular momentum and the relevant quantum symmetries must also be respected. The original positronium atom has no net electrical charge. The electron contributes negative charge, and the positron contributes an equal positive charge. Photons carry no electrical charge, so the final state remains neutral. The energy available comes mainly from the mass of the electron and positron. Positronium is bound, so the total energy is slightly lower than the energy of two completely separated particles. The binding difference is small compared with their combined mass energy, but precision calculations include it. Any motion of the positronium atom also contributes. An atom travelling through the laboratory carries kinetic energy and momentum. The photons produced in its annihilation must reflect that movement. An atom at rest provides the simplest case. Suppose positronium annihilates, while its overall centre is nearly motionless. Its usual decay produces two photons. Since the original atom has almost no total momentum, the combined momentum of the two photons must also be almost zero. A photon always carries momentum in the direction it travels. Two photons can cancel each other only if they move in opposite directions with matching momentum. One photon travels one way, the other travels the other way. Each carries close to half of the available energy. For an electron and positron pair with very little motion, that amount is close to 511,000 electron volts for each photon. It is a familiar value in positron physics because it corresponds closely to the mass energy of one electron. The two-photon pattern is simple enough to be useful, but real measurements rarely produce two lines that are perfectly opposite and perfectly identical. The positronium atom may have been moving before annihilation. The electron and positron also possess internal motion while bound together. A nearby atom may absorb a small amount of momentum. A photon may scatter before reaching the detector. These effects alter the measured directions and energies. If the positronium was moving toward one detector, the photon travelling in that direction may be measured with slightly more energy, while the photon travelling backward may have slightly less. This is a form of Doppler shifting. The two directions may also differ slightly from a perfect straight line. Researchers call this acollinearity. Measuring that small departure can provide information about the motion of the electron and positron at the moment of annihilation. In solids, this becomes a powerful method for investigating electrons inside materials. A positron can annihilate with an electron belonging to the material. The outgoing photons retain information about the electron's momentum. By collecting many annihilation events and measuring the slight energy shifts or angular deviations, scientists can study the electronic structure of metals, semiconductors, crystals, and other substances. The disappearance of the positron therefore becomes a measurement of the particle it encountered. Positronium is not the only source of two-photon annihilation. A free positron can slow down in matter and annihilate directly with an electron without forming positronium first. Orthopositronium can also produce two photons through pick-off annihilation, when its positron annihilates with an electron from the surrounding material. The detector may see a similar pair of photons in all three cases. Timing and environmental information help distinguish them. Direct annihilation usually occurs soon after the positron has slowed. Positronium adds a short delay, although its average lifetime is only about 125 trillionths of a second. Pick-off annihilation may occur after a longer delay because it involves orthopositronium interacting with its surroundings. In empty space, orthopositronium has an average lifetime of about 142 billionths of a second, and predominantly produces 3 photons. A single photon might seem like an even simpler way for an electron and positron to annihilate, but a free pair cannot usually use that route. The problem is momentum. Imagine an electron and positron whose total momentum is 0. A single photon cannot remain motionless. Every photon travels at the speed of light and carries momentum. If only one were produced, the final state would have momentum in one direction, even though the initial state had none. That would violate conservation of momentum. Producing two photons solves the problem because their momenta can cancel. Inside matter, another object can sometimes take part. A nearby nucleus or atom can absorb recoil, allowing processes that would be impossible for an isolated pair. The environment becomes an additional participant in the conservation of momentum. For ordinary positronium in vacuum, however, the dominant annihilation patterns are determined by the spin and symmetry of the atom. Positronium usually produces two photons because its total spin and charge conjugation symmetry match an even photon final state. Positronium cannot normally use that fast two-photon route. Its usual decay produces three photons. The three-photon event is less orderly to look at, but it is still governed by exact rules. The original energy must equal the combined energy of all three photons. Their combined momentum must equal the original momentum of the positronium atom. Their angular momentum and quantum properties must match those of the orthostate. If the atom is at rest, the three photons cannot all travel along one straight line in a simple back-to-back arrangement. Their momenta must form a closed balance. A useful way to picture this is to imagine three people pulling on a ring with ropes. The ring remains at the centre only when the three pulls balance. One person may pull more strongly, but the directions and the other pulls must compensate. The photons share the energy in a similar way. They do not always divide it equally. One may carry a large portion, while the other two share the remainder. Another event may have a more even distribution. As long as the total energy and momentum are correct, many arrangements are possible. This produces a continuous range of photon energies rather than one narrow energy value for each photon. A detector recording the three-photon decay sees a broad distribution. The three photons also tend to lie in one plane when the positronium is at rest. Their directions can be reconstructed to test whether they balance properly. The probability of the decay depends on all the allowed arrangements. A three-particle final state has more variables than a two-particle final state, and the underlying interaction is more complicated. This helps explain why orthopositronium survives much longer than parapositronium. It has not been protected from annihilation completely. It has been denied the quickest ordinary route. The difference between 125 trillionths of a second and 142 billionths of a second is enormous at the atomic scale. The longer interval gives orthopositronium time to travel, collide, interact with fields, and respond to its environment. Annihilation may still occur at any point during that interval. The stated lifetime is an average. It is not a fixed duration assigned to every atom. One orthopositronium atom may decay soon after it forms. Another may survive longer than the average. Quantum mechanics predicts the probability of survival as time passes, not the precise moment chosen by an individual atom. If a laboratory creates a large group of identical positronium atoms at the same time, the number remaining decreases in a regular statistical pattern. At first, many atoms are present, so many annihilations occur. Later, fewer atoms remain, so the rate falls. Detectors convert this sequence into a lifetime spectrum. The experiment needs a starting signal. This may come from the arrival of a pulse of positrons at a target, or from a particle emitted by the same radioactive nucleus that released the positron. The stopping signal comes from the annihilation photons. The time difference between those signals is recorded for many events. A distribution gradually appears, showing prompt annihilation, short-lived parapositronium, longer-lived orthopositronium, and any additional effects caused by the material. Detectors do not usually capture a photon, as though placing it intact in a box. The photon interacts with matter inside the detector and transfers its energy. In one common process, it strikes an electron and scatters, giving part of its energy to that electron. In another, it transfers essentially all its energy to an electron in the detector material. The energetic electron then creates further excitations. In a scintillation detector, those excitations produce small flashes of visible or ultraviolet light. Light sensors convert the flashes into electrical signals. The size of the signal provides an estimate of the original photon energy. The arrival time reveals when the interaction occurred. An array of detectors around the source provides information about direction. Some systems use dense crystals chosen because they stop gamma rays efficiently and produce rapid flashes. Others use semiconductor detectors that can measure energy with greater precision. The best detector depends on whether the experiment prioritizes timing, energy resolution, position, or the ability to record several photons at once. No detector is perfect. A photon may pass through without interacting. It may scatter out of the detector after depositing only part of its energy. Several interactions may be recorded as separate events. Electronic noise can imitate a weak signal. Two photons arriving close together may be confused. Researchers use calibration sources, computer simulations, and detailed event selection to understand these limitations. Three-photon annihilation is especially demanding because all three photons should ideally be measured. Missing one can make the event look incomplete. A two-photon event in which one photon scatters twice may imitate three separate photons. Timing helps. Geometry helps. The measured energies help. A genuine event must satisfy all conservation requirements when the reconstructed particles are considered together. The detector is not simply counting flashes. It is testing whether those flashes can form a physically possible story. This type of reconstruction is important in searches for unusual positronium decays. The dominant modes are well understood. Parapositronium produces 2 photons. Orthopositronium produces 3. Higher photon counts are possible but rare. Parapositronium can produce 4 photons. Orthopositronium can produce 5. Each additional photon reduces the probability because the interaction requires more electromagnetic steps and occupies a smaller share of the possible decay rate. Experiments can compare measured rare decay frequencies with predictions from quantum electrodynamics. A mismatch might reveal an error in the calculation, an unrecognized detector effect, or a new interaction. The ordinary approach is to eliminate the first 2 possibilities before entertaining the third. Researchers also search for annihilation channels that would violate expected symmetries or produce particles that escape ordinary detectors. An invisible decay would appear as a positronium atom whose energy seemed to vanish from the apparatus. Energy would not actually be lost. It would be carried by particles that interact too weakly to register. Dark matter models sometimes provide candidates for such particles. Other proposals involve new light particles or a hidden counterpart of ordinary electromagnetism. No accepted experiment has shown that positronium has such a decay. Searchers instead place limits on how often it could happen. A convincing invisible event is difficult to establish. A normal photon may escape through a gap. A detector may fail. The positron may leave the intended region. Electrical noise may obscure a signal. Experiments designed for this purpose surround the annihilation region as completely as possible. They try to account for every ordinary way energy might escape detection. This turns absence into something measurable. The experiment asks how often a positronium atom appears to decay without depositing the energy expected from its photons. If that number is consistent with known detector losses, no new process is needed. The ordinary visible decays can test fundamental symmetries without requiring missing energy. For 3-photon annihilation, the directions of the photons can be arranged into quantities that depend on the spin direction of the original orthopositronium. Certain correlations would change sign if particular transformations were applied to the event. A transformation might reverse spatial directions, exchange matter with antimatter, or reverse the direction of time in the mathematical description. The standard model predicts that some combinations should be 0 or extraordinarily small. Measuring a non-zero result could indicate symmetry violation beyond known effects. These experiments need polarized positronium, meaning a group of atoms with a preferred spin orientation. They also require detectors capable of reconstructing the 3-photon geometry accurately. The analysis must account for interactions that can produce false asymmetries. Detector elements may not be placed perfectly symmetrically. One side may be more efficient. Photons may scatter in the target. The positron source may not be centered. A small experimental imbalance can imitate the signal being sought. The result depends on understanding the apparatus almost as carefully as the atom. Annihilation in matter adds another layer because the electron and positron involved may not have begun as partners. In pick-off annihilation, the positron from ortho-positronium encounters an electron in the surrounding substance. The spin arrangement of this new pair may permit a rapid 2-photon decay. The electron that originally belonged to the positronium does not annihilate in that event. It remains in the material. The atom has still been destroyed because one of its constituents has disappeared. Its former electron is no longer bound to a positron. Chemical quenching can also end positronium. The atom may react with a molecule or transfer its electron or positron in a way that breaks the original state. Spin exchange can convert orthopositronium into parapositronium, followed almost immediately by 2-photon annihilation. The measured lifetime inside a material is therefore not always the intrinsic vacuum lifetime. It reflects a competition between natural 3-photon decay, pick-off annihilation, spin conversion, and chemical interactions. Experiments with porous silica have directly observed positronium lifetimes shorter than the vacuum value, and have shown that surface interactions can influence annihilation in ways more complicated than a simple, pore size model. This sensitivity is why positron annihilation can reveal microscopic defects and empty spaces. A missing atom in a crystal creates a region with reduced positive charge from nuclei. A positron may become trapped there. Its annihilation signal changes because it encounters a different electron environment. Orthopositronium in a pore survives according to how often it reaches the walls and overlaps with outside electrons. Larger open regions can allow longer lifetimes. Chemical groups on the surface can shorten the lifetime through additional interactions. The final photons carry timing and momentum information from a location far smaller than any ordinary camera could resolve. In medical imaging, the 2-photon pattern allows the position of positron annihilation to be estimated. A radioactive tracer inside the body emits a positron. After travelling a short distance and losing energy, the positron annihilates with an electron, sometimes after forming positronium. 2 photons travel outward in nearly opposite directions. Detectors on opposite sides of the patient record their arrival. When 2 suitable signals occur within a very narrow timing window, the system identifies a line along which the annihilation probably occurred. Many such lines are collected and processed to reconstruct the tracer distribution. The image does not show positronium directly. It shows where positrons annihilated. Newer research aims to add lifetime information so that the local environment experienced before annihilation can also be studied. Reviews of positronium imaging report that a substantial fraction of positron annihilation in tissue can proceed through positronium formation, creating an opportunity to use its lifetime as an additional biological measurement. At the instant of annihilation, the personal history of the electron and positron comes to an end. The electron may have spent years inside an atom before being removed. The positron may have been created only moments earlier in radioactive decay. They may have formed positronium and moved together through a pore or vacuum. None of that history changes the requirement that the final particles conserve the complete physical accounting of the initial state. The photons leave at the speed of light. They scatter through the surrounding material. They may deposit energy in a detector, pass into the walls, or travel outward without being recorded. What remains in the laboratory is not an empty gap where the atom used to be. The surrounding fields and particles continue normally. The energy that once belonged to the positronium is now distributed among the annihilation products and anything that recoiled during the event. Matter and antimatter have not produced nothing. They have produced a new physical state with no remaining electron and positron. This distinction is important when antimatter is described as a source of energy. Annihilation can convert nearly all the original particle mass into the energy of outgoing particles, but producing antimatter requires energy in the first place. Collecting it is inefficient, storing it is difficult, and energetic photons are not convenient fuel that can simply be poured into an engine. CERN notes that present antimatter production is far too small for practical energy generation, and that the annihilation products would be difficult to convert efficiently into usable power. For positronium, the amount released by one atom is tiny. Its importance does not come from the quantity of energy. It comes from the precision of the event. The number of photons reveals the spin state. Their energies reveal the available mass and motion. Their directions reveal momentum. Their timing reveals the lifetime. Their correlations test quantum symmetries. Their interactions with detectors reveal where the atom disappeared. A positronium annihilation is brief, but it contains several layers of information. With enough events, physicists can test the most accurate theory of electromagnetic interactions, examine the internal structure of materials, improve medical imaging methods, and search for particles that have not yet been observed. The atom destroys itself, but its destruction is the part that can be measured most clearly. Learning to read those final photons turns positronium from a short-lived curiosity into a precise laboratory, and the results begin to answer a larger question about what this simple matter and antimatter system can reveal about the rules governing the rest of the universe. The final photons do more than mark the disappearance of positronium. Their timing, energy, direction, and polarization allow physicists to examine some of the most basic rules used to describe the universe. Positronium is valuable because it is simple in a very specific way. It contains only an electron and a positron. There is no proton with an internal collection of quarks and gluons. There is no neutron. There is no nuclear size to estimate, and no complicated nuclear motion to separate from the motion of the electron. This leaves a system governed almost entirely by the electromagnetic interaction. The theory used to describe that interaction is quantum electrodynamics. It explains how charged particles interact with light and with the electromagnetic field, and it is one of the most accurately tested theories in physics. A successful theory does not become exempt from further testing. The more accurate it appears to be, the more carefully scientists try to find the point where it may fail. Positronium offers a useful place to look because the calculations are both clean and demanding. The electron and positron attract each other. They move at speeds that require small relativistic corrections. They can exchange virtual photons. Their energy levels are shifted by fluctuations in the quantum vacuum. They can temporarily enter annihilation-related intermediate states and return to the atom before the final decay. Every one of those effects changes a measurable quantity by a small amount. Researchers can calculate the energy difference between atomic states, the separation between the para and author forms, and the average rate at which each form annihilates. Experiments then measure the same quantities. Agreement tells us that the theory is handling a matter and antimatter-bound state correctly. Disagreement tells us that something needs attention. The first possibility is usually an experimental effect. Positronium atoms move quickly, and their motion shifts the frequency of the light they absorb. Magnetic fields alter spin states. Electric fields distort excited atoms. Collisions with gas molecules or target surfaces change lifetimes and energy levels. Detectors have finite timing and energy resolution. The second possibility is a missing part of the calculation. Quantum electrodynamics is precise, but high precision requires many layers of correction. A term that is tiny in an ordinary calculation may matter when an experiment has reached the same level of accuracy. Only after those possibilities have been examined does the more interesting question become reasonable. Could the difference point to a particle or interaction not included in the standard model? This cautious order is essential. New physics is not the first explanation for an awkward result. It is the explanation left standing after ordinary physics, imperfect equipment, and human error have been thoroughly questioned, usually by several people, who would all prefer the apparatus to stop changing its mind. One of the main measurements is the interval between the lowest energy state and the next state of the same general type. Light can drive positronium from the lower state to the higher one when the frequency is correct. This transition is attractive for precision work because two photons can be absorbed together in opposite directions. Their motion-related shifts can partly cancel, allowing the internal energy difference to be measured more cleanly. Even then, the atom is difficult to study. It lives briefly, moves rapidly, and is usually produced in a spread of velocities. A laser that is perfectly tuned for one atom may appear slightly mistuned to another moving in a different direction. Recent experiments have improved the control of this process. In 2024, a research team demonstrated laser cooling of positronium. A carefully designed train of laser pulses reduced part of the velocity distribution to a temperature equivalent of roughly 1 degree above absolute zero in about 100 billionths of a second. That is still not a leisurely experiment. The cooling had to occur within the lifetime of orthopositronium. The laser pulses had to change frequency as the atoms slowed, repeatedly addressing the part of the cloud that was still moving too quickly. The achievement matters because slower atoms produce smaller motion-related shifts. They remain in an experimental region longer and can interact with lasers in a more controlled way. In 2026, another experiment reported a new continuous wave laser measurement of the lowest to second energy interval in orthopositronium, reaching a precision of a few parts in a billion. Results of this kind bring experiment closer to the accuracy of the best theoretical calculations and provide a clearer test of bound state quantum electrodynamics. The goal is not simply to add more decimal places. Each improved digit narrows the space in which an unknown interaction could hide. The energy difference between para and orthopositronium provides another test. This hyperfine splitting depends on the magnetic relationship between the electron and positron spins, relativistic corrections, vacuum effects, and contributions connected to annihilation. Unlike the hyperfine structure of hydrogen, it contains no uncertain nuclear magnetism. Both participants are fundamental leptons, and the calculation can focus directly on their interaction. Measurements have not always agreed perfectly with one another, or with theory. Some apparent discrepancies have weakened when methods improved, while others continue to motivate more accurate work. This is normal in precision physics. A disagreement is not a discovery by itself. It is an instruction to measure again in a different way. The annihilation lifetime provides a separate route. Quantum electrodynamics predicts how quickly parapositronium should decay into 2 photons, and how quickly orthopositronium should decay into 3. The prediction includes more than the simplest annihilation event. It must account for additional virtual interactions and rare corrections that slightly alter the rate. If the measured lifetime were reliably longer or shorter than expected, the difference could indicate an incomplete calculation or an additional decay process. The outgoing photons also allow physicists to test fundamental symmetries. A symmetry is a statement that the laws of physics retain a particular form when something in the description is changed. One operation replaces every particle with its antiparticle. Another reverses spatial directions as though the experiment were viewed in a mirror. A third reverses the direction of time in the mathematical description. The combined operation involving charge, parity, and time reversal occupies a central place in modern field theory. Under broad assumptions, the theories used in particle physics are expected to respect the combined symmetry. A confirmed violation would not be a minor adjustment. It would require a major change in the foundations of the theory. Orthopositronium provides a way to test this idea in a system made entirely from leptons. Researchers reconstruct the directions of the 3 annihilation photons and compare their arrangement with the spin of the original atom. Certain angular patterns should average to zero when the expected symmetries hold. A persistent non-zero pattern, after detector effects were removed, could be evidence of symmetry violation. Experiments using positron emission tomography style detectors have tested these patterns without finding a violation. Measurements reported during the first half of the 2020s reached sensitivity around 1 part in 10,000 for some correlations, and newer data sets have continued to improve the statistical precision. This does not prove that the symmetry can never fail. It tells us that any failure affecting those observables must be smaller than the experiment could detect. The connection to the matter and antimatter imbalance of the universe requires care. The observable universe contains much more ordinary matter than antimatter. Stars, planets, gas clouds, and people are made mainly from matter. If equal amounts of both had survived from the early universe, widespread annihilation would produce signals very different from what astronomers observe. Physics does include processes that treat matter and antimatter differently. Such violations have been measured in systems containing certain quarks. The known effects, however, do not appear sufficient by themselves to explain the cosmic imbalance. Positronium does not directly solve that problem. It contains equal amounts of matter and antimatter, and it exists only briefly. Its importance is that it permits precise tests of symmetry in the electron and positron sector. Should a new asymmetry appear there, it would expand our understanding of how matter and antimatter can differ. Even a null result is useful, because it rules out possible explanations and forces theories into a smaller range. Positronium can also search for new lightweight particles. An unknown particle that interacts weakly with electrons might alter the energy levels or decay rate. It could create a tiny additional force between the electron and positron. It might open a rare annihilation route unavailable in ordinary quantum electrodynamics. The clean structure of positronium makes such effects easier to identify than they would be in a complicated atom. One widely studied possibility is an invisible decay. In that event, positronium would disappear without producing the ordinary photons recorded by the detector. The energy would not truly vanish. It would be carried away by particles that interact too weakly with the apparatus to be seen. Proposed candidates include very light dark matter particles, dark photons, and particles belonging to a hidden or mirror sector. The details differ from one model to another, but the experimental signature is similar. The positronium forms, then the expected annihilation energy is missing. Searching for this is harder than it sounds. A normal photon may escape through a gap. It may pass through the detector without interacting. The positron may annihilate in the wrong part of the apparatus. An electronic signal may fail to register. The experiment must surround the formation region as completely as possible and calculate every ordinary way that energy could be missed. No accepted invisible decay of positronium has been observed. Existing searches place upper limits on how often it could happen. Those limits restrict the strength of possible links between ordinary particles and hidden sectors. A different unknown particle might not carry away all the energy. It could be emitted alongside a photon, or briefly influence the electron and positron before annihilation. Precision spectroscopy and decay measurements are sensitive to these possibilities in different mass ranges. This is why several types of positronium experiment remain valuable. One new interaction may shift an energy level, another may change a lifetime, another may distort the angular distribution of photons. A model that hides from one measurement may still appear in another. Gravity offers another question, although the experiment is much more difficult. Positronium contains one particle of matter and one particle of antimatter in equal proportions. It is electrically neutral, so a carefully prepared atom is less affected by uniform electric fields than a free positron would be. That makes it conceptually attractive for studying how a matter and antimatter system responds to gravity. The expected gravitational drop during the ordinary lifetime is extremely small. Positronium is light, fast, and short-lived. stray electric fields, magnetic effects, thermal radiation, and tiny surface forces can easily overwhelm the signal. Proposals therefore use cold positronium in highly excited states. Excitation can reduce the overlap between the electron and positron and allow the atom to survive longer. Slower atoms would have more time to fall before reaching a detector. No direct positronium free fall measurement has yet established its gravitational acceleration. The idea remains an experimental goal rather than a completed test. Laser cooling makes that goal less remote. Better control of speed and direction is exactly what a gravity experiment would need. Even so, extending the lifetime, limiting stray fields, and collecting enough atoms remain substantial challenges. A successful measurement would test a system different from antihydrogen. Antihydrogen contains an antiproton and a positron, so it is entirely antimatter and includes a composite hadronic particle. Positronium is half matter, half antimatter, and purely leptonic. The comparison would help determine whether gravity treats these different antimatter systems as expected. Another possibility appears when many positronium atoms are brought together at low temperature and high density. Positronium has an integer total spin in both its main forms, so a collection can behave as a gas of composite bosons. Bosons can occupy the same quantum state in large numbers. At sufficiently low temperature and sufficient density, they may form a Bose-Einstein condensate. No bulk positronium condensate has yet been produced. The atoms annihilate, and creating a dense cold gas before that happens is an exceptional technical problem. The successful laser cooling experiment is important because it addresses the temperature side of that problem. Stronger positron sources, efficient conversion, three-dimensional cooling, and careful control of spin states would still be needed. A condensate would allow scientists to examine a quantum state made from many matter and antimatter pairs acting collectively. It could provide new tests of positronium interactions and many body quantum physics. Some proposals have suggested that a suitably prepared condensate might produce coherent annihilation radiation. That remains speculative and far beyond current laboratory capability. It is a research possibility, not a device waiting for a larger power cable. Positronium also reveals information on a much larger scale. The centre of the Milky Way emits a strong gamma-ray line associated with electron and positron annihilation. Space-based instruments also detect the broad continuum produced when orthopositronium decays into 3 photons. The relative strength of the line and continuum shows that a large fraction of the galactic positrons form positronium before annihilation. Measurements have indicated a fraction close to 90% or higher in the central region. This tells astronomers about the gas in which the positrons slow down. The width of the annihilation line and the amount of positronium continuum depend on temperature, ionization, and the way positrons interact with atoms and electrons in interstellar space. The observations favour annihilation mainly in warm phases of the interstellar medium, rather than in extremely hot gas. The source of all those galactic positrons remains debated. Radioactive nuclei produced by stars and supernovae can release them. Compact objects can produce positrons in jets. High-energy particles can create them in collisions. More unusual proposals involve dark matter. The annihilation signal does not immediately reveal which source supplied each positron, because positrons can travel away from their birthplaces before slowing and disappearing. Positronium helps by describing the final environment. Its 3-photon continuum provides a record of the conditions where the journey ended, even when the place of origin remains uncertain. The same atom studied inside a vacuum chamber therefore appears naturally between the stars. Laboratory measurements of its decay spectrum help astronomers interpret the gamma rays reaching Earth. This connection works in both directions. Astronomy provides positronium under conditions impossible to build in a laboratory, spread across enormous volumes of interstellar gas. Laboratory physics provides the precise atomic and annihilation data needed to read the astronomical signal. Nothing about positronium alone answers every question. It has not explained dark matter. It has not revealed a failure of charge, parity, and time reversal symmetry. It has not shown that antimatter responds unusually to gravity. It has not solved the origin of the galactic positrons or the cosmic excess of matter. Its contribution is more disciplined. It turns broad questions into measurements. How accurately does quantum electrodynamics describe a bound particle and antiparticle? Do the electron and positron obey the expected symmetries? Can an unseen particle alter an atomic energy or carry away annihilation energy? Does a neutral system containing equal matter and antimatter fall as predicted? Can many short-lived atoms be cooled enough to share one quantum state? What conditions in interstellar space allow positrons to form atoms before they disappear? Each question uses the same simple object, but listens to a different part of its behavior. The energy levels examine the interaction while the atom exists. The lifetime measures the probability of its end. The photon directions and polarizations test symmetry. Missing energy searches for hidden products. Motion through a vacuum could test gravity. The galactic spectrum describes the environment around distant annihilations. Positronium lasts for only a small fraction of a second, yet the measurements connected to it reach from the structure of quantum fields to the center of the Milky Way. That range does not come from complexity. It comes from having almost nothing unnecessary in the system. One electron, one positron, no nucleus, and a final event that can be reconstructed in detail. The remaining question is less about what scientists can extract from the atom and more about how to understand its brief existence as a whole. It forms from particles that should destroy one another, behaves as an atom without the structure normally associated with atoms, and leaves behind a signal that can cross a laboratory or travel through the galaxy before being detected. Positronium does not remain in the world for long, but its short lifetime is enough to show us how much can happen inside an object made from only two particles. An electron and a positron meet. Their opposite charges attract. Under the right conditions, they lose enough energy to become bound together. For a brief interval, they form an atom with no nucleus, no protons, and no neutrons. Both particles move around a shared center, and that center contains nothing at all. The atom can occupy different energy states. It can absorb light. It can release light. Its two spins can combine in different ways. Those combinations determine how long the atom survives and how it is most likely to annihilate. Then the electron and positron disappear as particles, and their energy leaves in the form of photons. The whole sequence can last less time than a human nervous system could notice. Even the longer-lived form of ordinary positronium survives for only about 142 billionths of a second in empty space. That is not enough time to blink, move a finger, or become concerned that an atom has formed nearby without permission. It is still enough time for the laws of physics to act in full detail. The electrical attraction must be described correctly. The motion of both particles must be included. The energy states must follow quantum rules. Spin must be conserved. The allowed annihilation products must match the symmetry of the initial atom. The outgoing photons must carry the correct energy and momentum. Nothing is skipped because the event is brief. This is one of the useful lessons of positronium. The duration of an object does not determine the amount of physical structure it can possess. A thing does not need to survive for years to have energy levels, measurable properties, internal states, and a predictable pattern of behavior. Positronium is temporary, but it is not incomplete. During its existence, it is a genuine bound system. It is not merely an electron and positron passing close to one another. The particles share a quantum state. They behave as one neutral object. They can travel together through a vacuum or occupy a small space inside a material. If the atom is disturbed strongly enough, it may break apart. If it absorbs the right amount of light, it may enter an excited state. If it encounters a surface or a molecule, its lifetime may change. If nothing interferes, it eventually follows the annihilation path allowed by its spin. The paraform usually produces 2 photons and vanishes very quickly. The orthoform usually produces 3 photons and survives much longer. The difference comes from the way the electron and positron spins combine. The same two particles can therefore create atoms with very different futures. That fact is easy to state, but it represents something important about quantum physics. The identity of a system is not determined only by counting its ingredients. Two objects can contain one electron and one positron and still behave differently because their combined quantum state is different. The arrangement of spin changes the symmetry. The symmetry changes the allowed annihilation route. The allowed route changes the lifetime. The lifetime changes how the atom interacts with its surroundings and what scientists can learn from it. This chain of consequences begins with a property that cannot be seen directly and ends with signals recorded by detectors. A laboratory may observe two photons arriving from nearly opposite directions. It may record 3 photons sharing the available energy. It may measure the delay between the arrival of a positron and the final annihilation. From those signals, researchers reconstruct an event that no camera could ever photograph. They determine whether positronium formed. They estimate which spin state it occupied. They measure how long it survived. They examine whether its energy levels agree with theory. They search for rare events that should almost never occur. The atom is gone by the time the evidence arrives, but the evidence is precise. This makes positronium a useful example of how particle physics often works. Scientists do not always observe the object itself. They observe what the object leaves behind. A particle crosses a detector and deposits energy. An unstable atom produces photons. A collision creates a pattern of tracks. The original event is reconstructed from the consequences. The reconstruction is not guesswork. Every acceptable explanation must satisfy conservation laws and match the known behavior of the apparatus. Energy that appears in one detector must fit with energy recorded elsewhere. Directions must balance. Timing must make sense. An event that fails those tests is rejected or investigated as background. Positronium is especially helpful because its annihilation products are closely connected to its internal state. The final photons are not random debris. Their number, directions, energies, and timing carry information about the atom before it disappeared. This allows a system that cannot be stored in a bottle or held in a hand to become a precision scientific instrument. Inside a porous material, orthopositronium may survive longer in a large empty space and disappear sooner in a smaller one. Its lifetime can reveal gaps between molecules or defects inside a solid. Inside a liquid, surrounding molecules can push away from the atom and form a tiny region of lower density. Dissolved oxygen and other substances can change the spin or increase the annihilation rate. Inside biological tissue, those same effects may provide information about microscopic structure and chemistry. Researchers are investigating whether positronium lifetime measurements can add new detail to medical imaging based on positron emission. In empty space, the atom provides a cleaner test of fundamental theory. Without a surrounding material, there are fewer collisions and fewer outside electrons. The measured lifetime can be compared more directly with the prediction from quantum electrodynamics. Its energy levels can also be studied with lasers. Slowing the atoms improves those measurements because fast motion shifts the frequency of the light they absorb. Recent progress in laser cooling has shown that even an atom with such a short lifetime can be controlled before it annihilates. That does not make positronium easy to work with. Most positrons do not become useful positronium atoms in the exact state an experiment needs. Some annihilate before formation, some remain inside the target, some emerge in the wrong direction, some move too quickly, some decay before the laser arrives. The experiment must begin with many positrons to obtain a smaller number of useful events. Every improvement matters. A more efficient positron source provides more particles. A better target creates more positronium. A colder beam reduces motion-related effects. Faster detectors improve lifetime measurements. More complete detector coverage strengthens searches for missing energy. Progress usually comes from improving several stages at once. There is rarely one dramatic machine that solves the entire problem. There are sources, traps, targets, lasers, vacuum systems, magnetic fields, timing electronics, detectors and computer programs, all of which must work together. One component behaving badly can spoil the measurement. A small amount of gas left in the vacuum chamber can cause unwanted collisions. A magnetic field from nearby equipment can shift an energy level. A detector may record one side of the apparatus more efficiently than the other. A laser frequency may drift. The final result depends on understanding these effects and showing that they are smaller than the signal being measured. This is how positronium can test theories that already work extremely well. Quantum electrodynamics has survived many precise experiments, but positronium examines it in a special setting. The system contains a charged particle and its antiparticle. The particles have equal mass. Both move around the shared center. Annihilation contributes to the energy structure and the decay. There is no nucleus to complicate the calculation. A theory that describes ordinary atoms successfully must also describe this balanced matter, an antimatter atom. If it does, confidence in the theory grows. If it does not, physicists must find out why. The difference may come from an overlooked effect in the experiment. It may come from a calculation that needs another correction. In the most interesting case, it could come from an interaction that has not yet been discovered. No such interaction has been confirmed through positronium, but the search remains worthwhile. A new lightweight particle might change an energy level by a tiny amount. An unknown force might slightly alter the attraction between the electron and positron. A hidden particle might carry away energy during a rare annihilation. Each possibility produces a different experimental signature. Researchers therefore measure several properties rather than relying on one result. A new model may predict a change in the lifetime but no visible shift in the spectrum. Another may affect the photon directions. Another may allow an apparently invisible decay. The combined measurements restrict which ideas remain possible. Even results showing no unusual behavior are useful. They tell scientists that any unknown interaction must be weaker than the experiment could detect or must operate in a different way. Science advances by discovering new effects, but it also advances by closing doors that careful measurements have shown to be empty. Positronium can test symmetry in the same manner. The ordinary electromagnetic interaction places strong restrictions on which decays can occur. Parapositronium produces an even number of photons. Orthopositronium produces an odd number. Experiments look for forbidden or highly suppressed alternatives. They also study the arrangement of 3 photon decays to see whether the pattern respects expected transformations involving matter, antimatter, space, and time. So far, those tests have not revealed a confirmed violation. This does not mean the experiments failed. A measurement that finds no violation places a limit on how large an unknown effect could be. The next experiment attempts to make that limit smaller. The method can feel slow compared with the dramatic version of science often shown in films. There is no sudden alarm announcing that the laws of nature have changed. There are repeated measurements, control tests, calibrations, and long discussions about whether a small difference is physical or caused by a cable. That slower process is what makes the final claim reliable. Positronium also connects the laboratory to space. Electron and positron annihilation occurs throughout the universe. Astronomers observe gamma rays from the central regions of the Milky Way, with energies associated with the mass of the electron. They also observe the broader 3-photon signal expected when orthopositronium annihilates. These measurements show that many positrons form positronium before they disappear. The proportions of the narrow 2-photon signal and the broader 3-photon continuum help astronomers estimate the conditions in the gas where annihilation occurs. Temperature matters. Ionization matters. The density and composition of the gas matter. The signal suggests that much of the annihilation happens after positrons have slowed in relatively warm regions of interstellar space. Where all of those positrons originate remains uncertain. Radioactive material from stars can produce them. Exploding stars can contribute. Compact objects and high-energy jets may release them. Collisions involving cosmic rays can create them. More unusual explanations have also been proposed, including some connected to dark matter. The final annihilation signal describes where the positrons ended their journey, not necessarily where they began it. A positron may travel through magnetic fields and interstellar gas before slowing enough to form positronium. This makes the source problem difficult. Even so, the atom provides part of the answer. Its decay tells astronomers that matter and antimatter are forming temporary bound states in the space between stars. The same physics studied with a small target and a laser occurs across regions of the galaxy. An electron and positron meet. They form positronium. The atom survives briefly. It annihilates. Photons begin travelling through space. Some of those photons may continue for thousands of years before reaching a telescope near Earth. The atom existed for less than a millionth of the time required for its signal to cross even a small part of the galaxy. The evidence of its existence lasts far longer than the atom itself. That contrast is practical rather than mysterious. Photons can travel through empty space without decaying. Positronium cannot. It also gives us a useful way to think about what scientists mean when they say an object is real. Positronium does not need to be stable to be real. It does not need to exist long enough for anyone to see it directly. Its formation changes measurable outcomes. Its energy levels can be mapped. Its lifetime can be predicted. Its annihilation products can be detected. Its interaction with matter can reveal the size of microscopic spaces. An object with repeatable, measurable effects is not less real because it is temporary. Many familiar things are temporary as well. A sound exists only while pressure changes move through a material. A flame exists only while a reaction continues. A wave on water has no permanent object at its centre. Positronium is much shorter lived, but the general point remains. Stability is not a requirement for physical existence. The atom also corrects a common misunderstanding about antimatter. Matter and antimatter do not always annihilate at the first possible instant. They can scatter. They can form bound states. They can remain separated in electromagnetic traps. Their behavior depends on energy, motion, quantum state, and environment. Positronium represents the interval between meeting and destruction. That interval is short, yet it contains atomic structure. The electron and positron do not postpone annihilation because they are far apart in the ordinary ground state. Their quantum states overlap. Annihilation is possible throughout the lifetime. The delay comes from probability and symmetry. Parapositronium has a rapid allowed route and disappears quickly. Orthopositronium lacks that route under ordinary electromagnetic rules and must use the slower 3-photon process. The atom does not contain a physical clock counting down. Each moment carries a probability of decay. A large collection follows a predictable lifetime distribution, while the exact fate of one atom remains uncertain. This mixture of uncertainty and predictability appears throughout quantum mechanics. No one can announce the exact annihilation time of a particular positronium atom before it occurs. Scientists can still predict how many atoms from a large group will remain after a given interval. The individual event is uncertain. The population is regular. This is not a weakness in the theory. It is the kind of prediction the theory makes, and experiments confirm that statistical pattern with great precision. By this point, positronium may seem less like a strange exception, and more like a compact demonstration of modern physics. It involves antimatter. It requires quantum mechanics. Its energy and motion reflect special relativity. Its decay follows conservation laws and symmetry principles. Its photons are used in particle detectors and medical imaging. Its lifetime can examine materials. Its spectrum can test fundamental theory. Its formation in space contributes to gamma-ray astronomy. Few systems contain so much physics in so little material. One electron and one positron are enough. There is also a practical humility in the way positronium is studied. Physicists can describe its main structure extremely well, but precision reveals new layers of difficulty. Basic explanation takes only a few sentences. Opposite charges attract, a bound state forms, and the pair eventually annihilates. A complete calculation requires much more. The motion of both particles must be treated correctly. Relativistic effects must be included. Quantum fields modify the interaction. Virtual processes shift the energies. The possible annihilation states affect the spectrum. The simple atom becomes a demanding test because the measurements are so accurate. Nature often behaves this way. A system can be easy to describe approximately and difficult to describe perfectly. For most purposes, the approximate description is enough. To test the deepest parts of a theory, the small corrections become the main subject. Positronium gives researchers a place to study those corrections without the extra uncertainty of a nucleus. It may also offer future experiments that are not yet possible. Colder positronium could improve spectroscopy. Long-lived excited states could allow better control. Larger numbers of atoms could support a direct test of gravity. A dense, cold collection might allow many positronium atoms to occupy a shared quantum state. Better detectors could strengthen searches for invisible decays and symmetry violations. None of those goals is guaranteed to produce a surprising discovery. Their value comes from asking clear questions that nature can answer. For now, the established picture is already remarkable enough. A positron enters matter and slows down. It finds an electron. The surrounding environment removes the extra energy. A neutral atom forms without a nucleus. Its internal spin selects one of two main identities. The atom survives according to the allowed annihilation route. Its particles disappear. Photons carry away the energy. Detectors record the result. From those signals, scientists learn about quantum fields, materials, biological tissue, and distant parts of the galaxy. The atom does not need to know any of this. It simply follows the available laws. And here we are, much later by positronium standards, having followed its existence from formation to annihilation. You may be listening in a room filled with quiet, ordinary matter. Electrons are bound inside the atoms of the walls, the furniture, the air, and your own body. Almost none of them will encounter a positron tonight. Somewhere in a laboratory, though, a pulse of positrons may be moving toward a thin, porous target. A small fraction will capture electrons. Positronium atoms will leave the surface. Lasers will meet them. Detectors will wait for the final photons. Far beyond the laboratory, positrons are slowing in interstellar gas. Some will form the same short-lived atoms. Their annihilation light will begin a journey across the Milky Way. The process is small, but it is not isolated from the rest of physics. It belongs to the same universe as stars, medical scanners, quantum fields, and the atoms beside you now. Before we finish, you might consider the question from the beginning in a slightly different way. What should count as an atom? Must it have a nucleus? Must it appear on the periodic table? Must it survive long enough to become part of an object? Positronium answers no to all three. An atom can be a temporary bound state. Its center can contain no particle. Its two constituents can be matter and antimatter. Its existence can end through complete annihilation and still leave enough evidence for precise measurement. That is what positronium really is. It is not merely an electron colliding with a positron. It is the organized state they can form before annihilation. It is a neutral atom made from equal partners. It is a testing ground for the interaction between charged particles and light. It is a microscopic probe of empty space inside matter. It is part of the gamma-ray signal from our galaxy. Most of all, it is an example of how the universe can create stable rules without creating stable objects. If this quiet investigation has helped you relax, or has made the small world of particles feel a little more understandable, you can give the video a like and subscribe to Physics with William. It helps other curious listeners find these longer journeys through science. You can also leave a comment with where you are listening from and what time it is there. By now, more time has passed for you than an enormous number of positronium lifetimes placed one after another. The atoms would have formed and vanished before the first sentence was finished. Their photons, however, would still be moving. For the moment, there is nothing else you need to measure or remember. The electron has met the positron. The temporary atom has completed its brief existence. The detectors have received the final light. Let your attention settle back into the room around you. The ordinary atoms will remain where they are. The clocks can continue without supervision. Sleep well, fellow traveller, wherever you are listening from tonight.